Hello, good morning.
Good morning. How are you?
Yeah, hi, Shashik.
Great,
I'm fine.
great, Sanjay. So we'll start in another 5 minutes, just waiting for
Yeah,
other
yeah, sure.
participants. All right. So,
Good afternoon, all.
good afternoon.
Hello, good afternoon.
Good afternoon. All right, so it's time, I guess. Most of us are already here, so we can get started. So, yeah, good morning and good afternoon, depending on whichever time zone we are in. Uh, we'll just do a quick recap before we get started with today's content. So, in our last session, we tried to go to like start the analyze phase, wherein we discussed about different methods of calculating the process performance. Before we start performing the statistical test, we would like to check what is my performance level as of now. Once I improve it, I will again recheck my improved process performance in terms of sigma level, in terms of percentage, whatever may be the different metric, different ways I would like to calculate it. So pretty much we discussed about the different ways we calculate the process capability. First, we talked about the metrics we use in percentages. We talked about yield of the process, the throughput yield, and roll throughput yield. So the different ways, different percentage metrics to be used in different cases. So we discussed that yield is generally reported to the external client. Throughput yield is at stage level process performance, and roll throughput yield is again internal to you, but for an overall process performance. Now we are left with a couple of more ways which we will be working on. One is the CPK method, the sigma level method basically, and the DPO method. So there are different ways. If you know these all methods, practically you can check sigma level for any kind of data. So let's first get started with the process capability part of it with CPK that we talked about. So first thing, when we talk about process capability, we are talking about CP. The term that we use for process capability is called CP. The formula is very, very simple for CP. Again, we'll understand what does it mean and where do we use it and what's the inference out of it. Yeah, you have a question, PG Benabis?
No, no, no.
Okay, okay, perfect. Yep.
Sorry, I just turned on my mic.
Oh, that's fine. That's fine.
Yeah.
Okay. So the formula for CP is USL minus LSL divided by 6 standard deviation. That's the formula. Now, to be very honest and upfront, we do not end up using CP for various reasons too much, and we'll just understand that why. So it has got a lot of limitations. Before we use values to calculate CP, what does it mean? Let's understand what does it mean first. CP, it tells us the capability of the process to meet client requirements, but it doesn't tell us how we are performing. So bottom line, the question is the difference between talent and what do you do with the talent. Like practically you may be very, very capable, so you may be having a lot of capability, but what do you do with that talent is the real world impact, the performance. So difference between what you are capable of, what you can achieve. So I'm sure you all know a lot of talented people, but they are not so successful in their life. That's what we talk about. Like when we talk about process capability, it just tells you how capable is your process. Probably I'm in, say, manufacturing kind of industry, and I have a machine which can produce every day, say like 100 kilograms worth some product, and I'm only making it like making about 20 kilograms per day. So the capability is 100 kilograms, but what I'm dealing with it, like what I'm getting out of it is performance is only 20 kilograms. So it tells you the capability, how capable you are. So yes, the capability can be assessed, but it doesn't tell you how you're actually performing, which is what we want to know. So that's the biggest drawback of CP, that it tells you the capability but not how you're performing. The performance is not depicted by it. Second biggest drawback of performance process capability metric is it can only be calculated if you have both side specifications from client, like both USL and LSL. You need both. If you have one single site specification, you cannot calculate because you have both in the formula USL minus LSL divided by 6 standard deviation. So you have a process from which you will have your process data. You can calculate the standard deviation, but you need this USL and LSL from the client. The client will give you the USL and LSL. Like in the previous example, we talked about client gave us the limits. Like I need the marker, which has to be between 4.5 inches and 5.5 inches. The upper limit and lower limit was given by the client and always is given by the client. The client gives you a target and client tells you plus minus, this is okay with me. You need both in this case. When you're calculating CP, you need both USL and LSL. But unfortunately, there are a lot of metrics where you don't get two side specification. You only get a single side specification. So like for example, uh, sales target, you only get one single site specification. The client will tell you, I need minimum of $50,000 worth of sales. Nobody will tell you that you have the maximum you can do is 100,000. If you cross $100,000 worth of sales, I will penalize you. No. So minimum expectation is 50,000. If you don't do 50,000, well, that's a problem. I will penalize you. You're not meeting the target. But nobody will give you an upper limit that you cross this much of sales, I will penalize you. No, you will be my star performer. So you only get lower limit in case of sales data, like quality. I will only get lower limit. I need minimum quality of 90%. I will not say that, okay, minimum 90 and maximum 95. If you do more than 95, it's a defect. No, nobody will give you that. Like, for example, turnaround time or cycle time, whatever you may say, average handling time, whatever you may call it, various name, time related data. Always people will give you upper limit. Maximum time permitted to do this job is 15 days. If you can't do it within 15 days, if it take more time, I will penalize you. You're delaying the thing. If you can do it instantly, nobody will give you that. You must do it within, say, 1 day. If you do it before 1 day, well, I'll penalize you. Well, nobody will give you that. So sooner the better. So practically for time related data, nobody will give you a lower limit, but it will always say like maximum time permitted is this much. You must complete the job by this time. Nobody will give you minimum limit. Like defects. Well, maximum permitted defect is 2%. If you cross 2%, well, I will penalize you. But I would not say that you must have some defect. No, minimum defects I will not give you. It's good. You give me 100% quality, no defect. So such metrics, there are a lot of metrics where you only get a single side specification. You don't get both sides. So for such metrics, you cannot calculate CP because you need both. So that's my biggest drawback of CP. Now let's use basic values where you can get. Technically, when do you get a both side specification? Only generally when you're making a product which has dimensions. So products will give you, so you have dimensions, then you get two sides. When you like technically in the manufacturing industry, when you're manufacturing a product like those marker thing, got a specification. But for a lot of metrics, even in manufacturing, you have quality, you have sales, you have defects. These metrics will be a single side. Only when you kind of generally getting a product manufactured and you have length and breadth and dimensions like that, you will get two side specification. You're manufacturing a product. But rest of it, CP will be not required sort of thing because you can't calculate it. Uh, let's take the same example, the marker example. Let's see what is the CP that we had this targets and this thing. Let's kind of copy paste the information which we had. Okay, 4.5 inches, 5.5. Okay, let's use the same values and calculate what is the CP here. So for the same data, say USL given was 5.5, LSL was 4.5. This is what the client wanted. The product to be manufactured within limits of 4.5 and 5.5. Mean was 5.1 and standard deviation was 0.2. Well, in this formula, the problem is that we do not have mean. So this is not required actually in the process performance data like CP. You don't get it. So if you want to calculate CP, but just keep this in mind, when your CP value is less than 1, you have a defective process. Your process will have defects in it. You do not have good capability. The process is bad. When your CP is equal to 1, you are exactly meeting client requirement, but it's very dangerous. Like you right there, absolutely meeting, but you do not have cushion. You do not have luxury or for any bit of variation. The variation will happen. You will start making defect. CP value of greater than 1 is an excellent process where you desire an excellent process. That means your process has good capability and you can meet the client expectation. And even if there is variation in the process, still you will not create a defect. The benchmark in industry is CP value of 1.33. That's the like people who have metrics of CP, who have like technically in the manufacturing sector, they would at least want to have a CP value of 1.33 so that we have extra bit of cushion. And even if we end up making a product which has slight bit of variation, we still will be fine. Sort of, let me give you like show you an image so that how we can understand what does it mean. Say CP greater than 1, what does it mean? That the lower limit is here, the upper limit is here, and this is my process. So my process has a lot of cushion. I will not create defects. Even if the process shifts here, my process has slight variation, still will not create a defect. Even if process shifts here, still I will not create a defect. So because we have a lot of cushion, some bandwidth is here. This is where you get USL, LSL is a bigger value and 6 standard deviation is smaller value. So when you divide, when you use the formula, this is when you get a CP value greater than 1. Let me show you the image how it will look like in a CP less than 1. So this is your lower limit, this is your upper limit, and your process say is moving out. So a lot of some data is moving out. So you are creating defect. So it's going out of the process limits, like the customer's requirements. Your CP value will be deemed as less than 1. Now, one thing you ought to keep in mind, let's calculate this US CP value for the above product process. CP is equal to USL minus LSL. So USL was 5.5 minus LSL, which is 4.5. This is the numerator part, and then it says 6 standard deviation, 6 divided by multiplied by 0.2. So if you divide that, you get CP value here, which is going to be less than 1. CP value when less than 1, you always have a defect in your process. And yes, we had defect in the manufacturer, this marker thing. We talked about marker example. Yes, we had defect of 2.41%. This was a defective process. We calculated the yield of the process. It was 97.5, and there was a defect in the process. It was not meeting the requirement. So CP value less than 1 will always have a defective process, and that's when your process is not capable of meeting the expectation. Say client is expecting you to achieve certain process, but you by design you do not have the capability. Probably my machine that I'm using can manufacture only 50 kilograms, and your client is expecting 100 kilograms worth of production every day. Then CP is going to be less than 1. It's not capable by design to meet your requirement. But yes, it has got limitations. Hence, to solve that, to overcome the challenges, this CP was further kind of drilled down, and the real metric, the performance metric, was kind of created out of this. This is called CPK, which is called Process Capability Index. So that was CP was process capability. This is process capability index. It will solve both the limitation challenges. A, it will tell you how your process is actually performing, number one. B, it will give you the process sigma level, even if you have both side, even if you have only upper side, even if you have just lower side. You have any kind of data, you will be able to calculate the process sigma level process performance. Both side, single side, doesn't matter. So CPK can be calculated, and which will give you the sigma level. Let's understand what is the how do we calculate. It's a very, very simple one, but yes, let me first of all give you a clear image of what we are going to, when we get the formula, pretty much formula will help us solve it, but let's understand what does this formula mean. Uh, so this is, say, my process, and there is one client limit out here, and there's another client limit somewhere here. So if you remember, this is what we talked about. How do we calculate sigma level? You look at the process average and you see how many standard deviations can you fit between average and the target. That gives your sigma level. That's how we discussed about the pizza example also. It was like we were able to fit 6 standard deviations, so it was working at 6 sigma level. So that's how even formulas will calculate. So look at the process average, look at the target, and see how many standard deviations you can fit in. So assume you have both side, lower side, upper side, both side limits for now. uh, Say I'm just roughly drafting, like say we have 1 standard deviation, 2 standard deviation, 3 standard deviation, 4 standard deviation, 5 standard deviation, 6, 7, and 8. So my process is working at 8 sigma level on the upper side. We have another sigma level here also, because there's a client limit here also. So 1, 2, 3, 4, 5, 6, and 7. So my process is working at 7 sigma level on the lower side. Now, what is my final sigma? I can't add it up. That's not how it works. But bottom line, we're trying to understand A. If you have 2 side client limits, you will get 2 sigma levels. That's the first thing you got to keep in mind. If you have 2 side sigma level limits, then you will have 2 sigma levels out of it, and from which we will further calculate what's my final sigma, what is the overall sigma, which will report to the client. So A, that's one condition. When you have 2 side, then you'll calculate both side sigma. Secondly, if you have only, say, upper side only, then you will only calculate the upper side. If you have only lower side given, target given, then you'll only calculate the lower side. Then there will be no confusion. So A, you have there are formulas which will help you calculate the upper side sigma. There is a formula which will help you calculate the lower side sigma. If you have both side, then you will calculate both of them. Simple as that. So let's go back to well, I guess there is somebody who has asked. Okay, CP. Okay, CP. Okay, see, CP. When we talk about CP, it is something which tells you how capable the process is. Like I may come back and expect you to, say, start performing, and like I may give you an order when and you expected to deliver on that order, but the machines, the capability of your process is not actually equipped enough to deliver that order. I may be expecting too much from you. Then technically you are not capable to deliver the order. Probably I'm like, say it's in a very, very crude example, probably I'm talking about a Formula One racing, and I'm trying to probably drive my regular car in that Formula One racing. It is not by design capable to meet the requirements. It can't be used in a Formula One racing. So this tells you the design. Is it capable by design? How you performing will be explained by a different metric. But help us understand, like, is it actually capable to deliver it or not? So with that capability, like if we just use this formula, basically CP USL minus LSL divided by 6 standard deviation. USL will be given by the client, LSL will be given by the client. You need to have both of them for you to calculate the CP part of it. If you don't have it, then you can't calculate CP. Simple as that. You need to have both. So these two values will come from the client. 6 standard deviation, how is the standard deviation calculated? From your process. So you pick up your process data, calculate the standard deviation, and just plug in the values. So in this example that we talked about, we had this client requirement which was given as, like, we need markers which will be like maximum to 5.5 inches, lowest up to 4.4 inches. This was USL minus LSL, which was the client expectation. And how we were performing 6 standard deviation, which is like 6 multiplied by this. It gave us CP value less than 1. And we saw that it was a defective process. When we calculated the quality of the process, we saw the yield of the process was not 100%, it was less. So we had a defective process, and that's what it validates. When you're capable, by design, you're not capable to meet the requirement, you will have a CP less than 1. Is it okay, Tahir?
Yeah, thank you.
Okay, thanks. Now, coming back to the process capability index part of it, now we will try to understand, like, say, we know there are two levels of sigma, like we will be getting CP upper limit, the upper side sigma. The formula is USL minus mean because it's upper side divided by 3 standard deviation. 3 because we only talk about half of the process, not the full. So only towards the upper half, 1, 2, 3, plus 1, plus 2, plus 3. So that's the upper side sigma level formula. And the lower side sigma level formula is CP LSL towards the lower side, mean minus LSL divided by 3 standard deviation. So keep this in mind. If you have both side limits given by the client, then you will use both the formula. You'll calculate, you'll get a sigma level, upper sigma, lower sigma, and then from which you will further calculate the sigma level. If you have only upper side, then use this formula. Then this formula will not be used. If you have only lower side target given to you, then you will use this formula. So it solves that problem of both side specification. Now comes CPK. What will be my CPK? CPK is the minimum of CP USL or CPLSL. Whichever is minimum becomes the CPK. So you calculate this value, you calculate this value, and whichever becomes the minimum will be your CPK. If you have only upper side, then there is no choice. That will become CPK. If you have only lower side, that will become CPK because there is no choice there. But if you have a choice, because then you will be calculating both, you have to pick the minimum as CPK. Now that will bring us to the next thing, which is Z bench, or you can call it as ZLT, or you can call it as long-term sigma. Various nomenclatures, but that's how, so you can, what is this long-term sigma? We'll understand that. For now, CPK, whatever value you get as CPK, you multiply that with 3. It will give you your long-term sigma. We'll understand what is long-term, but for now, just the calculation part is what we're trying to focus on. Once you have calculated long-term, then there is called ZST or current sigma, or you can call it as short-term sigma. How do you get that? Because you have calculated long-term in the first step, you need to add 1.5 fixed sigma value. That will give you your current sigma level. So that's the simplest formula that we have. Uh, we can look at this current sigma level from this one. So now a couple of things we will definitely like to understand here before we move ahead. Again, I will explain that, but let me kind of reiterate this. You use this formula for calculating upper side, use this formula for calculating lower side. Minimum of them will become CPK. Whatever value you get as CPK, you multiply with 3 to get your long-term sigma. I'll explain what is long-term. And when you get long-term, you just need to add 1.5 to it. This is fixed 1.5, which will give you current sigma level. Why 1.5 and all that stuff, I'll explain that. But for now, let's calculate one like with the same example, same values. What is the sigma level for this marker example when we calculated the defect percentage, when we calculated yield, when we looked at the CP? What is the sigma level for this marker example? Let's have a look at it. Upper limit was 5.5 minus mean. Mean is 5.1. That's my numerator. And denominator will be, it says 3 standard deviations. So 3 multiplied by 0.2. So if you remember, this is what we had. So USL is 5.5 minus mean, which is 5.1, divided by, so we have to divide further, and divided by 3 standard deviations. 3 multiplied by 0.2. That will give me, so let's divide this. This is my upper limit capability. This divided by this. This is CPUSL. This is upper side capability of the process. Let's calculate the lower side also. Lower side is mean, which is 5.1, minus LSL, which is 4.5. This is what we have in the numerator part. Let me just, okay, now, and this is 3 standard deviations. 3 multiplied by 0.2 will give me this value. So pretty much I have now the lower side capability also. So that's my upper, this is my lower. I just need to follow the values and put the values and I'll be able to calculate it. What is my CPK? Minimum of them is the CPK. So just like to reiterate, if we have only upper side, then this would have become a CPK. If we have only lower side, then this would have become a CPK. But because we have both, then minimum has to be chosen. So CPK will be minimum, which is, this is my CPK. This is lowest. That's my CPK. What do I do with my CPK? You multiply with 3 to get your long-term sigma. So you multiply this with 3, that gives you long-term sigma, and you add 1.5 in this. This is your current sigma level of the process. So your process is working at 3.5 sigma level. That's how you calculate. So yeah, just the explanation, I will do it, but I think uh, question wise, like if I look at these values, I hope it is not a typical one. It's not a difficult one for us to calculate the sigma levels. Is it okay with everyone?
Yes.
Okay.
Yes,
Okay.
yes.
So I'm going to leave this formula right here. I'll be off for like a minute while I'm giving a quick for like a question for you to kind of, because this kind of questions could come in exam, and so I'm giving you some values. Please have a look at these and you can calculate, and please ping on your chat while I'm back. And this is what we have. And mean is 145, standard deviation of 15. Please calculate the current sigma. You have all the formula right in front of you. You can use these values. I am going to be on mute for a minute. I'll be back. So in the meantime, please just solve it and put it on the chat, whatever answer you get for current sigma, the final sigma.
Hello, Mr. Sash. I'm not
Yeah.
able to follow it. What's ZLT?
Long-term sigma. ZLT is long-term sigma.
Okay.
So, okay, long-term sigma is ZLT here. ZLT is long-term sigma. So you calculate
Thank you.
you call it a Z bench, or you call it a ZLT or long-term sigma. Practically, these are symbols. Okay.
Okay, okay.
All right. So I'll be back in a minute. Please just calculate in the meantime. Tahi says 4.5 is the current sigma. Okay. How about others? In the meantime, I'll just sort of get started. I'm sure you all must have started already. USL. I will check the chat or whatever like we have all shared. So just give me one quick second. We'll just check it out if I've done it correctly. Perfect, perfect. We've got it correct. Absolutely correct. Om Prakash ji, pure short term is perfect. Yes, you're correct. Said yours is also correct. Nofal, you were correct. Perfect. 3.8, perfect, Subodh. And like everyone got it correct. Tahir, you need to look at it. 4.5 is not the correct one. Okay, let's kind of, most of us have got it correct. Let's just quickly have a look at it and understand where did we go wrong in case we have. So the USL minus mean. So USL is 180 minus mean, which is 145, divided by 3 standard deviation. So 3 multiplied by 15. So we divide this, we get 0.77, whatever this value. Then this is mean divided by mean minus LSL. So mean is 145 minus LSL is 100 divided by 3 standard deviation. So we get this value of 1. The minimum becomes the CPK. We multiply that CPK with 3. This is what we do, CPK with 3. So it gives you this value. So CPK multiplied by 3 gives you long-term sigma, and you add 1.5 to this to get the current sigma level. Now, that's how we get the sigma levels calculated. Now, few things I must explain so that we all understand why, like what are these values? What is the meaning of long-term? So first of all, you look at this something called Z bench or ZLT or long term. We're talking about long term sigma. You look at ZST, current sigma, short term sigma, it means the same. So different ways people call this level of sigma level. Now, few questions we must understand. What is this long term? What is this short term? And what is this 1.5? So we should get clarity about it. And then we'll also use MINITAB to calculate the sigma level. First thing, let's understand what is long term and short term. See, in a reality, and that's what in reality, there's only the sigma level, which is the sigma. It comes from the formula is the long-term sigma. This is the real sigma level. Having said that, what is used and practiced by everyone is the current sigma level. Now, what is the story behind it? Because Motorola started this so-called Six Sigma process, uh, and you can see there is a difference between long term and short term is of 1.5. So current sigma has extra 1.5 and the long term sigma has less. So when we report, and that's what, please just pay attention, when we say Six Sigma, whenever people report, always the Six Sigma process, whenever people say Six Sigma process or my process working at Six Sigma level, everyone always reports your current sigma. Everyone reports current sigma level. So that means if this is the case, whenever people report, they have added 1.5 in long term, because from the long term itself, you are able to calculate the sigma level here. So from the formula will give you long term. This is a manual addition, not from the calculation. This is coming from manual addition. This is coming from the formula, but this is where it's manually added. And what's the story? I'll just explain that. So whenever people, any software, even Minitab is used for calculation of sigma level, it will always give you long term. This is the real sigma level. This will come from software also. Minitab will give you this value only. Formulas will give you this value. What these people did when they calculated created the sigma level process, and they observed a lot of process, and every process used to kind of deviate plus minus. Some process used to get better, some process used to get lower, but by the virtue of time, keep this in mind, everything deteriorates with time. You buy a new car, it will not give you problem initially, but over a period of time it starts giving you problem. So wear and tear happens over a period of time. It happens with people, it happens with process. When you're young, you can do a lot of work, but as you grow old, you do not have that kind of capability, or like you can't work for those many long hours. So everything deteriorates with time. Same happens with the process also. So these guys observed a lot of processes, like thousands of processes. They've looked at various metrics, and they saw that on an average, keep this in mind, the word is on an average, not exact, on an average, every process deviated and lost about 1.5 sigma. So that was the drop sort of thing between current and the long-term sigma. So every process tend to, and what is the definition of over a period of time? There's no set definition. It's a debatable topic. World is divided into two sort of people, like two blocks. Some people say this is irrelevant and we should not be even talking about it because this is it doesn't make sense. Not every process will go down by 1.5. Some will go up, some will go down, some, like, so it's an average, not exact for everything. So Motorola sort of created this, and this became a culture. So a lot of people still debate, and I'm one of them who debates, and I still believe this is the real sigma level. And even we'll look at some tables with some data, it always looks at long term. This you have to do manually in every case. Whether you're calculating manually, software, this has to be done manually. So you need to add 1.5 to get the current sigma level. So when we report that process is working at 6 sigma level, technically what does that mean? So this is all same. 6 sigma current is equal to 4.5 long-term sigma. So when we report the process as 6 sigma, actually it's working at 4.5 long-term sigma, because we have added 1.5 and reporting it as 6 sigma, which means that 99.99966% quality is at this level. So this is same level. And when we say 3.4 defects in a million opportunity, that is at 4.5 long-term sigma. You are talking about the same thing in multiple language. So I might say 1 hour is equal to 60 minutes is equal to 3600 seconds. So even if you report your process performance as 3.4 defects in a million, or you say 99.9966 whatever percent, or you say 4.5 long term, or you say current sigma 6, practically you're talking about the same level of performance. It is just that Motorola people created this sort of thing. It's debatable, highly debatable, but as a general practice, everyone uses this. So even though, unless and until you specifically tell that this is, I am reporting long term, then it makes sense. Otherwise, whenever people say 6 sigma or any kind of sigma level, they have always added 1.5 to this. So keep this in mind. This is how it is. And to validate it, so that we all know how to calculate. So we know the process of calculating sigma level. Just have a quick look at the material that we had shared, and that has certain things in it. So training material folder, data files, if you go to that analyze folder, in this you have, and I would request you to please do the same at your end also, there is capability test folder. If we check this out, there's something called Z table or Z table. You open this Z table, this is sigma level table, sigma level. And let me just enlarge this, okay, yeah. And this is long term. There's nothing called short term table. You have to manually. This is from GE, General Electric. So this is a long term table. These are all sigma levels. This is all sigma. This table is all about long term sigma. Every table is all about long term. There's nothing called short term. Now, how do we know what sigma level, how to read the sigma level from this table? Please just have a look at it. First thing first, let's understand about the 6 sigma, because that's what we all have been dealing with. If I'm saying it's a long-term table, Six Sigma long-term, like Six Sigma in long-term will be 4.5 Sigma. So because that's what we talked about, right? Because we add 1.5 and we report 6 Sigma. So what is the value of 4.5 Sigma? Let's have a look at it. 4.5. 4.5 Sigma. Look at this. 3.40 E006. How do you read these values? Let's understand it. So it says 3.40 E006. That's how it says. That's what we have here in this table. 4.5 long term is 6 sigma, which it says as 3.40 E006. Let's read. Let's see how do we read it. The way we read it is 3.4 defects and in 10 to the power. That means how many? 6 zeros. We got why? Because whatever exponential value you have, 6. So 3.4 defects in a million opportunity is 6 sigma level. That's what we report. And if you the other way is 3.4 defects, 1 followed by whatever value you see here. 6 means 6 zeros. 1, 2, 3, 4, 5, 6. That's what it means. 3.4 defects in a million opportunity. That's how you read this. Let's read some other sigma level also. Let's randomly, first of all, randomly pick up any number, and I want to calculate the sigma level for that and see how many defects do we make at that level of sigma. So if I want to calculate, say, sigma level for 2.87 sigma, this is what, and keep this in mind, this is 2.87, which I'm reporting as current. We always talk about current. So what will be my long-term sigma? It will be less 2.87 minus 1.5. That is what I will be able to see here. 1.37 long term is 2.87 sigma. So let's see how many defects do we make at 1.37 long term or 2.87, meaning is same. Let's read 1.37. Let's go 1.3. 1.3 is here, but 7 will come from the top. Let's look at this. 1.3 and 7 from the top. This is the value. See, 0.07 from the top and 1.3 from here. It says 8.53 E002. 8.53 E002. Let's write it down. 8.53 E002. How do you write this? Can anyone tell me how many defects do we make at this level of sigma? How many defects? How do I write this? How many defects am I making at this level of sigma?
8.53.
And how many opportunities?
100.
Absolutely. 1 followed by 2 zeros. Yeah. Because we have 2 here. That means 8.53%. This is, if I make 8.53 defects out of 100, it's 8.53%. At this level of sigma, my defect rate is 8.53%. You can calculate sigma level for anything, defect rate for anything. Let's pick up any random and I can something else. 3.45 sigma. Well, 3.45 sigma. Let's convert this into, first of all, long term. That's 1.95. Let's go back to the table. 1.95. 1.9 is here. 5 will come from the top. This is 2.56 E002. 2.56 E002. So it's 2.56 E002. So it's 2.56 defect in a million opportunities. Or not, sorry, my bad. 10 to the power 2 is 100. So out of every 100 opportunities I will make, so my defect rate is 2.56%. At this level of sigma, this is my defect rate. Now let's look at something else also. Let's say we are talking about 5.84 sigma. 5.84. This minus 1.5 will give me the long term. 4.34 sigma. Let's check 4.34. 4.3 is here and 4 will come from the top. So this is 4.30, 4.31, 32, 33, and 4.34. Where it says 7.12 E006. So 7.12 E006, whatever, 006. Oops, my bad.
So 7.2 defects and 1 million opportunities.
Absolutely, yes. 7.12 defects out of every 1 million opportunity. This is how we read this. You can calculate sigma level for anything. Sigma level, look at the number of defects. This is all defect table. Sigma level is defect measuring table. These are all defects. When we say 6 sigma, technically 6 sigma will be 7.5 sigma, because this 6 sigma is long term. So at 6 sigma, you will be making some in billion. Look at this. This is whatever. I don't know. I'm sorry, I'm bad at those numbers, but 9.87 defects out of whatever this, one followed by 10 zeros. Whatever number you see, those are the number of zeros after one. I hope everyone is okay with this.
Yes.
Okay. So this is how we calculate the sigma level, like CPK and all that. So practically it helps you to
One
understand.
clarification.
Yeah,
So
yeah.
6 sigma, if you are telling it, always it should be calculated to subtract with the long term, and then we need to look up.
Yeah. So the table will only see, everything will give you. See, unfortunately, this is how it is. So people always report sigma level. Whenever you will also report your performance, you have to add 1.5, because be it the formula method or be MINITAB, you will always get long term. So you need to add 1.5 to get your current sigma and reports current sigma. But if somebody would ask you what is the defect you're making at that sigma, so you know what's the method. So you always like look at the long term, because every table will give you long term. MINITAB will always give you long term. So this has to be calculated from the long term only.
What is this 4.5 into ZLT?
I'm sorry.
4.5 into ZLT you have done, right? 6 sigma correct above.
This one, right? So
Yes.
6 sigma is equal to 4.5 long term. So 4.5 long term plus 1.5 will be 6 sigma. So either you say 6 sigma or you say 4.5 long term, meaning is same. I say 1 hour or I say 60 minutes, meaning is same. It's just a 1.5 we have added to it. Nothing else. There's no change in the performance. The performance at this level, if you say in this language of long term or you say in the language of short term, performance level still remains the same.
Suppose if I am telling my process is 6 sigma, then we need to subtract 1.5 and then go for the long term, correct? Or
Yes. So when you're reporting, say my process is 6 sigma process. So you are reporting that your 6 sigma process is there. So this is the performance level which you're reporting. If somebody would ask you how many defects would you make at this level of sigma, then you know, because it's current, you need to look for your long-term sigma out of it. So this is my long-term sigma. Now refer to your table and find your defect rate at this performance level. So 6 sigma means long term 4.5, which means we will be making 3.4 defects in a million opportunity. Does that clarify? Anyone has any question, please do let me know. We can clarify this. We can go over with some more examples in this.
I have question related to CP and CPK.
Yeah, please tell me.
As you told me that CP value is, if it's less than 1, it means our process is not good.
Yeah, by design. By design, it's not
But by design, yeah. Oh, what is the use of CPK? It's only used for measuring Six Sigma levels.
it's used for checking the performance level. So well, see, this is, I had both the limits. I was able to calculate what is my sigma level here, right? We were able to
Yeah.
calculate. If we had only one side limit, still I would have used one side formula and I would have calculated my sigma level. If I had like, so this helps you calculate the sigma level. CP tells you the capability, how capable you are, but doesn't tell you how you're performing. Why? Because there is nothing called mean here. It doesn't tell you where the process is centered. There's nothing called mean here. It is not in the formula. You need mean to tell you the formula is like how good your process is. Center of the process is not like CPK tells you the performance, how you actually performing. It doesn't tell you the capability. Capability comes from CP. How capable is your process? But a lot of metrics you cannot even calculate it. In the end, what we are interested always is what is my performance level? How am I performing? And when we look at CPK, that gives me a clear idea of how am I performing. I can calculate my performance level here. Does that like give you the basic difference? CP tells you the capability, this tells you the performance index, how you actually performing. the performance level.
Yeah, as it's the name CPK process capability index,
Right.
and CP is only process capability.
Capability. It just tells you the capability. Like as I said, like the difference between talent and what do you do with the talent. I may be very, very skilled, but if I just keep sleeping at home and do nothing, I'm wasting the talent. So the talent is the process capability, but what I do with it in real world, and this is what it means, the performance, process capability index. That's what everyone wants to know. What is your sigma level? How you're performing? How good or bad? So this can help you understand how good or bad. You get your sigma level, you get to know what's the performance level.
Yeah, thank you.
Okay. And pretty much before we go to MINITAB for this calculation, the last method of calculating and the easiest one out of them is looking at DPMO method. So this is another way we calculate sigma level, probably the easiest of all of them. Defect per million opportunity. So you just need to know the defect rate to calculate the sigma level in this case. The formula is very simple. Say if I call for a meeting, there is a meeting which I've called and 50 people are supposed to come for a meeting. 45 people came on time. What is the defect here? 5 people who were late or who did not come up. That's my defect. What is the sigma level for this particular meeting? The meeting that I called, what is the sigma level for that? Formula is simple. Norm sin V, NORM, norm sin V. Open up the bracket. Formula is 1 minus, now whatever is the defect rate, 5 people who were late, that's defect, divided by what was the total opportunity, 50. If we close this will, if I hit enter, it will give me long-term sigma, but I want to see the current sigma, plus 1.5. Now meeting whatever formula. Okay, well, I messed up with something where, okay, probably the bracket.
You need another bracket.
Yeah, plus 1.5 is what I want. Okay, do I want?
Yeah, you need another bracket after. You need double bracket after 50.
Okay, I guess so. Yes, I probably am.
Two brackets should be there.
Yes, and I guess this can be eliminated now. Yes, sorry, my bad. So norm sin V is, this is what I have for any sigma for anything. Like let's say if I have a process which has 27% defect, what is the sigma level for this? If I have 27% defect, simple, norm sin V, open up the bracket, 1 minus, open up the bracket. Now what is the defect rate? 27 out of 100. Close the bracket, close the bracket, plus 1.5 for current sigma. That all I'll report. 27% defect, that means my process is working at current sigma of 2.11. That's, it's simple as that. Well, I will take irrational number. Let's say I have a process where I found 1342 defects in 1600, whatever, these many opportunities, any random number. Well, no hassle, same formula, norm sin V, anything that comes to your mind.
Hello, Mr. Sash. The,
Sorry, I got kicked out and I'm back. Sorry. Let's kind of. Yeah, I hope I'm audible.
Yes, now, yes.
Yes.
Oh yeah. Okay.
yeah.
Yeah. You had a question. Somebody had a question the moment I got kicked out.
Can we try with the same marker example?
Yeah. Sure. Like say, norm sin V. How many defects did we had there? Like that was some defect rate we got there, right? 2.41% defect, right? So 2.41 defect out of So norms in V1 minus 2.41 defects out of 100.
Hello, Mr. Sash.
Yeah,
I just want to ask a question.
yeah.
How do I know if my sigma is good or bad?
So see, sigma, it just tells you the level that you're performing. Higher the sigma, better it is. See, you would always want to increase the quality of your process, reduce the defect. So technically, there's no limit for having a sigma. Higher the better. You maybe say if I'm at 95% quality, I would definitely want to make it better, 96, 97, 98, 99. So it's never end to it. How so it's that's why it's a part of a continuous improvement plan. It's a never ending journey. You would always try to get better with time. So Six Sigma projects could go into multiple projects. So you do one project, achieve a target, sustain that level, again look for another higher level where you further reduce the defect. You continually increase the process by multiple doing like multiple process projects, one after another, which will keep challenging with yourself within the next project to improve the metric further. Lesser the defect, again there's no end to it. So there's nothing called good or bad. Technically you would always like to remove the defect from the process, make it more sustainable with less variation. So the higher the better technically.
Uh, oh, I see. Thanks for that.
Okay. Okay.
Does
So
the above formula and this formula will be the same result will be there, or it will be
yeah,
a
yeah, see,
different?
see with the this thing 3.5 is what we got, like current sigma CPK. This is what we got, marker example.
Okay.
Yeah, 3.5 sigma. This is, you round it off, it will become 3.5. Oops, the other way around. Yeah, that's how we got 2.41% defect. Is it clear?
Okay.
Same norms in V formula. 2.41% defect was there, right? This is what we calculated, 2.41% defect. Yeah, this is the one. Marker example, the defect rate was 2.41%. So if we use the same formula, same thing, we calculated the sigma level using CPK. We got 3.5 sigma for that marker example, 3.5 sigma, and using norm SINV formula, we got this for marker example. So we use the same values here, 2.41% defect out of 100, and gives me this.
Okay.
Okay. I hope that's okay with everyone. We can move
Yeah,
on to MINITAB.
Yes.
yeah, that's okay. I just
Yeah.
want to ask, why do we use only USL in CPK?
Uh,
Don't
in
we need to use also the LSL
we
for
use that
computing CPK?
we use for depending on the CPK part of it, like so in CPK the reason why we choose minimum, it's not only like if LSL is lower then we'll pick LSL, whichever is minimum. Let's understand
Oh, I see.
why. Yeah, whichever is minimum has to be chosen. So the reason why is, like, if you just take a very small example, say this is a road, that's my LSL and USL. This is my road, what I'm driving on, and this is my car, which is my process. Now that's the car that I'm driving. Now here I have less bandwidth, here I have more bandwidth. Which will I be more concerned with? This side, because I may hit the road on the less is this side. So I'm more concerned with this, not concerned with this one. In a real world, say this way, probably I'm working at 6 sigma level. This side I'm working at 2 sigma level. I cannot report 6 sigma level to my client. That means I'm barely making no defect, and whereas I will be making a lot of defect on this side. So we always report the realistic number, not a rosy picture to the client. So wherever this minimum, we give the real picture to the client, because client will be coming back and shouting at us in both the cases. So like if you have the defect, this side, the client will not give you a problem that you're crossing the upper limit because you got a lot of bandwidth. You're working at 6 sigma level on the upper side, but here you are working at 2 sigma. That means you're making a lot of defect on this side. You should be reporting the real number, not the 6 sigma one. That's why minimum is chosen. I hope we are clear with this.
Yeah, that's great.
Perfect.
Thanks for that.
Okay. Let's then quickly have a look at how do we calculate this using MINITAB. And so for that, we already have this file, this data for simulation project, this particular file. Let's have a look at this IT ticket closure time, the same file. I'll just quickly use this and let's understand how do we read this. Okay, so this is my problem data like that I have collected at the end of measure phase. They copy paste this data on MINITAB. That's the time data. So for management, as I said, management will always give us the time, like the criteria, upper limit, lower limit will always be defined by the client. So how do we calculate sigma level for this? So like we go to stat, we go to quality tools, and here we go down till capability analysis. And the first thing says normal. So capability analysis, normal. Just click on this. Now it is asking what data you want to check. Well, I want to check this ticket closure time. So double click this, it'll come here. Now it's asking what is the subgroup size. My subgroup size is single, number one. Why? Because I'm collecting one data at a time, one data. If I have been collecting two samples at a time, it will be two subgroup. Three, this is three subgroup. Single column, technically we're talking about a single subgroup. Generally, it's always one. Now, what is the specification limit? Lower specification limit, upper specification limit. So in case of like a manufacturing kind of example, you will get both side. In this case, time related data, management has only given us one side. So in this case, management has given us a target that 20 minutes is the maximum time. You should not cross 20 minutes, otherwise it's a defect. We would like to do a project to reduce the ticket closure time, the turnaround time, cycle time. We want to reduce that. Maximum time permitted is 20. So the management gives you the target. This is your target given by the management. You want to reduce the project, like the time. That's what we have here. Now we will come back and make some changes there in this, but for now I'm just clicking OK. That's it. We don't have a lower limit. Click OK. We'll make some changes with this to further understand what we get here. So let me just enlarge this also so that we can read the information. Okay. So first of all, if I look at this is my maximum limit, upper limit. This line, whatever. Sorry, pardon for that. That's 20 minutes. Anything more than 20, there's a lot of data actually, which is crossing the upper limit. This is all defect. This is all defect. This is 100%. Anything less than 20 is good. This is the problem area. A lot of data, 20 minutes, more than 20 minutes, defect. So it's clearly visible in the data that we have a lot of defect here. Lower limit, no. Upper target, technically we don't have a specific target. We have a maximum thing which has been given. We need to bring it down less than 20. Sample average is 18. Sample count is 181. Now, there are two standard deviations. We all know what is standard deviation. For now, I will explain, but yes, for now, just keep this in mind. We always look at within. I'll explain the other part of it, definitely. For now, just concentrate on the within part, standard deviation within. Now, when we look at this within part, we will come back again within here also. So once we're done with the within, I'll explain the overall and this overall, I'll explain that. But let's look at it. CP cannot be calculated because you need both USL and LSL. So nothing, CP cannot be calculated. CPL, lower limit, cannot be calculated because you don't have a lower limit. Upper limit was calculated and CPK minimum, the same minimum, because there is no choice. The same became CPK. That's how we get this value CPK here. Now, at this level of performance, what is the number of defects you make? How many defects are you going to make? Again, we're looking at within. We're not looking at overall. We'll come back to overall later. At this level of sigma level or performance level, you can convert this into multiply with 3 to get long-term sigma plus 1.5 will give you current sigma. So CPK, you get it here. At this level of sigma, whatever you get here, it says that you will be making ppm stands for parts per million, defects in a million. So at this rate, you will be making how many defects in a million? 369,080 defects in a million opportunity. At this level of sigma, you'll be making these many defects. That's what it means. Now, let me just go back and make some changes which you would ideally like to do. I would rather like to see sigma level directly, but not the current. Current cannot be achieved. So at least the long term CPK, but I want long term also. Let's close this chart. Oops, let me just get rid of this. Now, when we were filling all these details, I can click on options. Now it says capability analysis. This is what we were getting, capability analysis, but it also gives you option of looking at sigma level directly, but long term. You click select this one. That's it. Default, it's selected capability, the CP part, but we would like to look at sigma level directly. That's it. Click OK. And now the chart will the same chart, but you have extra information. You'd have less work to do. Yes, current you still have to calculate. You don't have the CPK multiplied with real Z bench. Z bench we all know. So it's same, rest everything is same. Z bench you get, which is long term. You add 1.5 in this, you will get your current sigma level. So that's your long term sigma, which is 0.33. Current sigma will be plus 1.5, which is 1.83 is your current sigma. Long term is 0.33. That's your CPK, that's your defect rate. Is everyone okay with it for now? I'll explain the other part of it, the PPK, this overall within, I'll explain that, but okay, I'll just repeat the steps once again. Let me just quickly do this. So that's the data. I go to stat, I go to quality tools, and then I go to capability analysis. And the first one is normal. I want to do it. This one is normal. Click on normal. Now, first is this data I want to select. I select this data. Subgroup size default always will be 1 because a single column, 1. Say if you are dealing with lower limit, then put the lower limit. If you're dealing with upper limit, in this case, time related data, only upper limit, maximum limit permitted is this. Like sales data, you would have minimum sales, then you will put the target here. So either you have lower limit, you have upper limit. If you have both, then put both and put it here. Like say, let's say just random example, assume this data is something else and we have both limit. We have limits of say 14 as lower limit and 20 as upper limit. Subodh, are you kind of using a different MINITAB version probably? Oh yeah. So see, there are certain like what values, how different is that? Okay, let me quickly like just complete this, and I'll like you can share your screen. Just give me one quick second. So options, I select the benchmark sigma and just click OK. So I'm putting both sides right now, just to kind of show you both side sigma level. So you can put it both ways also, like depending on what kind of expectation the client has, what kind of process you're dealing with. So you can put one side, two side. So it tells me that your sigma level is this, and because we got CPK and then pretty much you get your both side sigma, and technically you get 1.5 added to this and you get your long-term sigma. Now have a look at this. It says on the lower side you'll be making these many defects, on the upper side you'll be making these many defects at this level of sigma. Your total number of defects in a million at this level of sigma will be this much. So simple as that. This is how you get it. Now I'll quickly stop sharing. Subodh, can you share your screen? I'm just like kind of getting rid of this. Just share your screen. Let's quickly have a look at this.
Yeah, just a minute, Shashi.
Yeah, sure. Are you using 17 by any chance?
No, I think it's 19 only.
Okay.
It's not 17. It's the new version.
Okay.
So yeah, can you see my screen now?
Yes.
Yes. So this is the values that I'm getting, because the values over here is a little different, and my standard deviation also was showing difference from what you were sharing. But these values for the Z bench and USL and CPK seem to be the same.
Probably the ones you just downloaded, mine needs to be updated. I have probably not updated it for some time. So probably there's some sort of revision they might have done in the backend, because you must have downloaded it now, right?
Yeah, a week back.
Yeah, so yours is an updated one, definitely, yes. So mine, like I have not got it updated for some time, and so that could be the possible reason, but the process is exactly the same. So yes, that could be the reason, because we saw similar glitch when people were still working on 17, but and versus 19. So sort of an updation, but there's some sort of update going on. But yes, the process is clear, and the method is pretty much like, so it looks clear, like what we're looking at. Okay.
Right. Okay. Thank you.
Thanks. Dan. You can stop the sharing and I'll just take it over. Okay.
Yes.
Now, going back to this now, pretty much now, what are these additional values when we talk about PPK? Here we're talking about what is this standard deviation within and overall, and versus what we're looking at is within and overall. What is that? Now, having said that, we know the process of doing it, but let's quickly understand what is this additional stuff we are looking at. Now there is something we, oops, okay, that will sort of, okay. Now, the one we were talking about, what we are seeing there, we have already looked at what is CP. CP, we already know what is CPK, we also know that. So let's kind of put it here, CP, and we know CPK. Similarly, we have PP, and we have PPK. Now, CP is process capability. So we already have the formula, process capability. This is CPK is process capability index. PP stands for process performance. This is process performance index. Now, the formula for CP, let's kind of get this from the top. Here we got, this is the formula for CP. And actually, let's copy paste it here. So this is the formula for CP, and this is the formula for PP. Same stuff, no difference. What is the formula for CPK? We have it here. So CPK is, this is what we get for CPK. Just copy paste it here. That's the formula for CPK, and that's the formula for PPK. Now they'll just kind of change this CP to PP, PPUSL. This will become PPLSL, and this will become PPK. Now that's the only difference. Minimum of, so this will be PPLSL. Now the question will definitely come. Now formulas are same. When you look at CP and the formula of PP, it's the same. The formula for CPK and PPK is same. Then why do we see a difference in the CPK and PPK? The only reason why we see a difference in CPK and PPK because of standard deviation. The way standard deviation gets calculated, this uses within standard deviation. This one uses standard deviation, which is overall. That's the only reason why there is a difference in the values. Now, whenever whatever values we see, there's slight difference in the sigma levels. Why? Because the standard deviation which is used in the calculation of within versus what is used in overall is picked up from the standard deviation. That's the only thing which is playing the role here. Now, when do we use like how this standard deviation gets calculated? Sort of out of scope for us, honestly, but I'll sort of quickly give you a quick glimpse of it so that we know, we understand this. Okay. This is one data. So I'll just sort of give you a quick idea about this one so that we understand what is the basic difference. Some data that we have here. If I want to calculate what is within. So if I want to calculate standard deviation here for this row, this is within one subgroup. One subgroup, this is the standard deviation. Within all the subgroups, this is the standard deviation. And I take the average of all these standard deviations. This is within standard deviation. That's an example sort of a thing. And what is the overall one? I will take standard deviation here. I'll pick all of them. There will be a difference in the values. Look at the standard deviation values, this versus this. So different ways how standard deviation gets calculated, which one gets used where, that's what we need to understand. We will, in a Six Sigma project, will never ever come across the PPK. We'll always use the CPK. What is the difference? We'll see, when you are dealing with a project, you do not have the bandwidth to wait for like 6 months or 1 year to report your process performance. You will collect data for like 15 days, 20 days, and you will do your analysis and get the process, like you will evaluate your process. So your data is a short-term data. CPK is coming from a short-term data, like 10 days, 15 days, 20 days data, month data at the max. You're collecting short-term data. Your process has not seen all up and down, like seasonality, people, market trends, everything. So process goes through multiple things over a period of 1 year. But CPK will be picked up from a very short-term data. So it is why it uses the within standard deviation, which is a short-term, very small data set. So small variations are captured when you're looking at CPK. Your process may not have seen all possible variations in 1 month period, but in Six Sigma projects, when you're dealing with projects, you end up improving a process on a short-term period. Like you continue to collect data, make changes, continue to collect data, analyze it, and take decisions. So you're doing it on a short-term basis. You always deal with CPK. Once you have improved the process, it's stabilized, controlled, it's running smoothly. When you have sort of collected 1 year long data, that's when you have something like a population data, a huge data. That's when you start reporting your PPK. That's more of a stable process sigma, because that 1 year long data would have seen all up and down, seasonality, trend, people, machine, whatever can go wrong or good in the process, the data has all seen up and down. So this is more of a stable sigma level over a period of time. So when we start referring to this overall standard deviation, when we have captured almost all possible variations in the data in technically 1 year long time frame. So this is when process is improved, controlled, stabilized, and that's running for good 1 long year. That's when you can say overall, this is my stable sigma level for my process. That's where my process stands. This is short-term, volatile, dynamic, short-term period. You improve, make change, you do things, you move on. So projects always deal with CPK. This is when your process has turned into operation, project to operations, regular day-to-day business world. But yeah, long-term data, short-term data. That's the basic difference. We will not come across this, but yeah, when you view the business or view the decision maker in your organization, you have improved the process. You kind of collecting data on a regular basis. Over a period of time, you may start looking at PPK as your sigma level of the process. But in a project, no. In a project, we'll always be looking at within short-term data. I hope that's, yeah.
Suppose the initial machine throughout, if you want to take it 100 numbers of this one, in this CPK need to be done, its machine is installed. Brand new machine, process is established. So we need to look it out for CPK or PPK.
No, CPK, see, technically, PPK means a huge long-term data, long-term, because the process has not seen all up and down. I don't know, machine is brand new, but it may sort of, and it will sort of give you some up and down over a period of time. So always a CPK. The process will, the same data gets reported later on as PPK. See, PPK will be more of a performance data, which is like a long-term sustainable data. So this machine, which is probably not giving you a lot of issues, wear and tear, but when you start using it over a period of time, it may start giving you wear and tear. You will start understanding that when the process starts like sort of breaking up, machine gets like starts giving you error, or it starts creating issues, it gets heated up. So that sort of process data, which was captured over a period of time, then you start reporting the PPK. But initially, it's always the CPK. Short-term data will always be a CPK. Do not go for a PPK practically unless and until you have historical relevance, a huge data that you can rely on. Then definitely, then you can start using PPK. Technically, there is no such difference, but in a project, Six Sigma project, we always look at CPK, not the PPK version. Is it okay with everyone?
Is there any time frame fixed for a PPK?
I'll say at least a year. At least a year. See, I'll see, because the process sees there is a lot of things which impact. When you're talking about PPK, we are generally reporting a stable, confirmed sort of sigma. My process, and ideally, your process should not have a huge difference between CPK and PPK values. If your process has huge difference between CPK and PPK values, that means it's not stable. Technically, even if I collect a data for 1 year, your sigma level should look similar to what your data looks in a 15 days data period. If there is a lot of variation in 15 days data sigma versus 1 year long data sigma, that means your process is not stable. So when you look at this chart, it automatically explains this. Have a look at this. These dotted lines. So you see dotted lines. This is for overall, this is for within. If there's a huge gap in them, then you have a big problem. This should be very, very close. This standard deviation should be very, very close. So even if you pick a 15 days data, it should give you a clear picture about the process, as it will be like in a month, year-long data, or a month data, 6 months data. If there is a huge variations, then you are dealing with a process which is not yet stable. You need to improve that process with the help of sigma levels, and control measures and all that stuff will be required.
So therefore, for the current example, it shows that the process is somehow inefficient. Is
Sort of,
somehow
yes.
inefficient.
Yes, and so process has a lot of challenges. In this case, the process has a lot of challenges. A lot of defects are there. But yes, the process variation is not too much, like not too much of differences there in there, but it's not capable for sure. There's a lot of data going out of lower limit, a lot of data going out of upper limit. So the process has a lot of challenges. Yes, we need to reduce the variation in the process so that we can meet the expectations from the client.
So that means the population is PPK and the sample is CPK we can take.
Absolutely, yes, sir. Absolutely. Is it okay with everyone? Like, or probably if in case you have any questions, we can definitely take it up right now.
I just want to ask the table below, the expected within and expected
Which
uh,
one?
on the MINITAB,
On the MINITAB.
on the
This
graph,
one. This one, right?
on the bottom part. This
Yeah,
yeah,
same stuff.
performance.
Like within, if you're referring to the PPK values, then you will look at the sigma levels here. What is the number of defects you would be expecting at this level of sigma, which will go less than the low, like how many defects you will make on the lower side, how many defects would be making on the upper side. So this one is calling for the upper side, and this is for the lower side.
Are these defects?
Yeah, there are number of defects at this level of sigma. How many defects would you be making
Oh,
at
I
this
see.
level of sigma? How many defects would you be making?
That's by millions, right?
Yeah, absolutely. PPM stands for parts per million in a million opportunity. Because
I
Six
see.
Sigma is always on a million scale.
Okay.
Okay.
Cool. Yeah. Thanks.
Perfect. Thanks. Having said that, like for everyone, the same thing in a report version. Have a look at this. Assistant, capability analysis. Click on this. It goes to the first one, says capability, CPK, PPK. Click on this. Process data is in one column. Yes. We select this process data. Subgroup size 1. We have a single subgroup, same stuff. What is the specification limit, lower, upper? So we have 20 as specification limit. That's it. Click OK. Your report version is ready. It gives you the PPK version on a long-term scale. It gives you the defect rate of your process. Let me just enlarge this for now. Yeah. So it gives you the PP, PPK, Z bench, and all that stuff, what we're looking at. You want to make some notation on your own, double click, add your comments in here, click OK, say it gives you long term only. So the current sigma on the process. So you can make some stuff notations here, make a personalized report for yourself, click OK, you're done. Just scroll down. We haven't studied control charts, but yes, it gives you control charts also. We'll study them in the last session. Yes. So it gives you the control chart of your process. It has done the normality testing of the process. We know the data is normal looking at it. Anderson Darling test. It gives you a comprehensive report. So this is when you have a process performance report. So 3 reports, 3 pages, just copy paste. This gives you complete stuff, the PPK version, the CPK version. Technically you have all the information, a much clearer presentable report than the previous one, which you can use definitely. So that is the crude way of doing it. But yes, this is the reporting version which MINITAB offers for you to kind of share the report. Like you can just do a right click, share it wherever you want, take it. I hope this is clear to everyone. Like this is a few clicks, same values, same information that we put in there. Is that okay with everyone? Is everyone okay with the question? Like anyone has any questions?
Can you come down? There is a
This one?
report. Yes.
It just gives you the same stuff like stability, what are the number of subgroups. When you talk about the control charts, that's how it's going to be picked up from.
Okay, it's a standard. It's nothing to do.
Yeah. No. Just basically, it just tells you what does it mean, the words that will be used there. So it just sort of a nomenclature. You say glossary sort of thing.
Okay.
So it generates like whenever you, and for other reporting features that will be you learning from here, it will always be generating some sort of report card. Technically, it's a glossary sort of thing. So for people to understand, because when you talk about stability here, this is where we are trying. They're basically trying to refer to stability of the process in this case, like the control charts and all. Like when we study control charts, it'll get clear automatically. But yeah, is everyone okay with it? I hope.
Yeah, it's cool.
Okay,
Yes,
okay,
yes.
perfect. Now, before, like, we shall be taking a break in another 5 minutes, but before we go on a break, let's quickly move on to like 7 QC tools. Just briefly tell you about this, and when we come back, we'll talk with the Sigma level sort of journey. But yes, 7 QC tools, 7 quality control tools. There are a few which we already know, so that we know when we come back, what are we going to be looking into? Histogram, check sheet, flow chart,
Ishikawa
Pareto.
diagram.
Yes, your fishbone diagram or Ishikawa, then scatter plot,
Work breakdown scatter.
and finally you have control charts. So 7 quality control tools. So now quickly, just wanted to run through this. Histogram. Now, when we talk about histogram, we have already done this multiple times. Can anyone tell me when did we study histogram? We've already done that, by the way.
Yeah, I just want to try. If
The
you want to review your historical data,
Yeah, so normal distribution is nothing else than your histogram. Why do you have histogram? Like the same data, you have this histogram. You make this graphical summary. That's your histogram. When you look at histogram, what you are able to study is this is your histogram, normal distribution. Your mean plus minus 1, plus minus 2, standard 3 standard deviations. You just want to have the histogram created only, then refer to this again. So practically, when we talk about histogram, we've already done this, but now we're just trying to put together the same normal distribution. That is your histogram. Why do we create a histogram? We already know it because we've used this histogram so far. Why, when we look at this normal distribution, what do we get to know? The central tendency. What is we when we looked at histogram, we looked at mean of the data. We also end up studying the variation in the data, variation, central tendency, and the variation, which is we look at left at with standard deviations. We don't have histogram. How are you going to calculate the sigma levels? So for sigma level calculation, you need to have the lower limit, upper limit calculated. Again, you need to have the distribution spread first, and then you put the limits so you can calculate sigma level. So histogram is by default being used in whatever we do. Technically, that's how we have always already started looking at yield of the calculate process or sigma level calculation. We have used histogram already. Check sheet is something which we have all been using. Check sheet is sort of to-do list kind of thing. Like it's a pre-recorded values where you record information. Even this data collection thing is a check sheet. Attendance register is a check sheet. Like any kind of auditing piece format is a check sheet. We have all like used check sheets in various formats. Even the housekeeping guys, they maintain a check sheet which says 8 o'clock they have cleaned, 9 o'clock they have cleaned it, 10 o'clock. So sort of an auditing sheet. Flow chart, we've talked about already. The SIPOC diagram or a flow chart like could be a process mapping. We all know what is flow chart. These are basic commonsensical stuff which we know, like we have sort of used it for a pretty long time in some shape or form. But the ones which we definitely want to cover up is Pareto chart. We'll be covering up. This is referred as 80-20 rule. We'll come back and do this work on this one. We'll do it on MINITAB. Learn how to do it on MINITAB. Fishbone diagram we've already done on MINITAB already. Scatter plot, we will not be doing it now. We will be doing it with one of the hypothesis tests. We will be dealing with correlation tests. So when we do study correlation, this is going to be the graphical plot. This is the statistical test. This is going to be the graphical test for that. So correlation is always done with scatter plot. So correlation, scatter plot are combined. So that's when it'll get covered. Control charts we'll study in control phase. So once we come back from the break, we will be covering a Pareto chart. And after that, we will start with the hypothesis part, when we will be left with, after this Pareto chart, we'll be left with, say, have to cover up these things. Then we'll get into the hypothesis testing. So I guess we all good. Everyone we have the same page. Is that okay with everyone? Let's then take a 30 minutes break, whatever time zone we're in, and let's be back in 30 minutes from now. All right.
Okay.
Thank you. Thank you.
Okay, thank you. It's 30 minutes, right?
Yes, 30 minutes. 30.
Okay.
30. All right.
Thank you.
जीमेल पे किसने लिखा है कि रिचार्ज करना है? ये करेक्टर में नहीं लिखी हो, ये सब जीमेल पे ढूंढ जाओगी तुम। बहुत जीमेल में। हाँ हाँ जल्दी जल्दी से ये बता दो। एक मिनट बोल अभी लंच में टाइम पे बस खत्म होने जा रहा है। मेरा टेंशन है अभी। हाँ क्या लिखा गया यार? क्या लिखा रही है? कूलर दिखा रही है, टूटा कूलर वो करना कूलर है। कूलर दिखा रही है, टूटा कूलर। हाँ तब ये है रोटी में लगा रहा है। अभी इसमें गर्म हो गया, इसमें कुछ नहीं देख लो। इसमें से कुछ तवा कुछ नहीं गर्म किया, इसमें से निकालना है गर्म करके। इसमें से ये देखो, इसमें गर्म हो गया कि नहीं देखो। राजा हो गया राजा। अबे कौन खाया इसे? देखो पर चार्ट कोड के रिशु हाँ यार चार्ट कोड के खाओ। चार्ट कोड के अभी हाँ हम शादी के टाइम में दही चाट के खाए थे। हम दही हम शादी में चाट के खाए थे। किसी से शर्म नहीं, चाट के अच्छा से पूरा सपोर्ट के खाए थे। सपोर्ट के हाँ रिशु से बात कर दो, क्या किया जल्दी। हाँ क्या हो गया जल्दी बता दो। सुबह से क्या किए? हाँ तो सब खत्म कर लो सब कुछ, फिर क्लास आगे से चलेगा। मालूम है ना 11 से? मालूम है ना? हाँ तो अपना सब तैयारी कर लो और सब एग्जाम का तैयारी करो। अपना मॉडल पेपर से कर रहे हो नहीं? सब तैयारी सैंपल पेपर हैं? हाँ ठीक है गुड। और अभी अब क्या करोगे? अभी क्या प्लान है? ओके चलो ठीक, अभी ब्रेक कितना मिनट का है? हाँ तो अब उसके बाद अब ब्रेक नहीं है, अभी हो गया ब्रेक, अब कुछ नहीं, ठीक है? कितना ब्रेक? वो तो 10 मिनट का होता है। आधा घंटा का नहीं भाई, एग्जाम आ गया, आधा घंटा का नहीं चलेगा। 10 मिनट का है। क्योंकि क्योंकि एकदम सिर पे आ गया एग्जाम में सब। अच्छा मामा दे दो, जाओ जाओ ब्रेक। हाँ भाई पिठा पिठा का पिठा है खत्म कर। है तो यार हमको दे दो, सब पी जाएंगे। निशा दाल पी लो, दाल पी लो। निशा निशा से बात करो। निशा आला नहीं, आला नहीं। हाँ निशा क्या क्या हो गया? ठीक है तो अभी आप ब्रेक लेने आ रहे हैं? कौन सा ऑनलाइन? कौन सा सब्जेक्ट? ठीक है, वर्कशीट आया है? हाँ तो करो, ठीक है। खाना खाना खा लिया? निशा का खाना देखा मैं, दाल छोड़े उसमें। नहीं नहीं नहीं, आधे घंटे का एकदम मैं बोल देता हूँ, दे दो, बता देता हूँ। रीसा आधा घंटा का दाल पिएगी, ठीक है? कितना नहीं बहुत पैसा वाला हो गई हो, कितने लगो तो बोल रही फेंक देंगे। रीसा बोल देगी बोल दी दाल फेंकने के लिए। हाँ गोविंदपुरी बैंक की सबसे पैसा वाली है। इधर चाय पे बुलाता है। अंदर जाके कितना बड़ा कर दिया ऐसे करके। हाँ? एक झटका में कैसे अरे राम राम अब बोलने दे देना हो जाएगी लड़ाई जाएगी आपको इसमें क्या बेच रहे हैं क्या मेरी की खबर है तो भाई हाँ तो दिखाएंगे ना दुबई में तुम जाओगे दुबई में कहीं से भी देखोगे तो बुर्ज खलीफा दिखाई देगा वहां जाके फोटो खिंचवा क्या बोले 12 पे 12 उसका तो है अरे भदौड़िया क्या नाम है उसका
Hello.
Yes. Yeah. I hope everyone is back from the break.
Yeah,
Yeah.
Okay. All right. So next we'll get started with the Pareto chart, was one of the 7 quality control tools, and barring this again with the scatter plot and control chart will come in the due course of time. So there's a file in this folder, like the data files for class. In the analyze folder, we have this file by the name of Pareto chart. We open up this file, you will see sample data. So that's how the data needs to be collected for you to do a Pareto chart on MINITAB. So like we can take any example, we can use this one or this one. Let's use this, say, defects. So we need to have type of defects on the one column and the count of defects. How many times did that defect happen? So that's how the data needs to be collected. So I'll just copy paste this data and just paste it on MINITAB. So you have the types of issues and the count of issues. How many times did that defect happen? Now, what is this Pareto chart going to do is it will help you prioritize which defect needs to be prioritized more in terms of frequency. Technically, I can see it right here. Uh, uh, it doesn't need, like, so a lot of people still argue about this logic, like why we need a Pareto chart when we know which one is the highest problem here, like, in which is but yes, it's always said that like a picture is worth 1,000 words. So it's good to have an image for this data. That's how it looks like. So we have got data like how many times did a particular issue happen, and we have the count of it. So to get this done, we go to Stat, Quality Tools. And the second one is Pareto Chart. So we click on the Pareto chart here. That's asking what is the defect type, the type of the defect. So we put in the defect here. Frequencies will get the counts. So we put in the count. It's asking us another, like by default, we have always, it's selected like post 95%. We look at that, combine everything. So we prefer not to combine. We want to see everything clearly. So we prefer not to combine. There's no harm keeping it that way also, but yeah, we would like to see Pareto chart the way it is. Let's kind of enlarge this and understand. Now, Pareto chart, when you do use MINITAB, you will see it will create this data, rearrange the data into descending order. The maximum problem will come first, the second highest will come second, third highest, fourth highest. It is not necessary for you to keep them in order in the sheet. Like if you look at the sheet, the data was in different order. Like if I go back to the sheet, see 274, 59, 19, 43, it was in a different order. It was not in a descending order. But when I look at this thing, it has already created it in a descending order. I don't have to sort this for doing it on MINITAB. So the highest problem comes first, second highest, third highest, fourth highest, and so on and so forth. So it gives you the count of what, as you have in the sheet, same count in a descending order. Then it gives you the percentage. Now, how much is this 274 of the total number of defects? So it's like 64.8% of issues come from missing screws. So 274 is 64.8% of the total number of issues. This is 13.9% of the total number of issues, the missing clips. 10.2% is contributed by leaking cascades. So technically, I get to know what is the total contribution of each and every issue to the total. So we can get this done, like we can sum it up and divide by this, well, like this divided by the total will give you these percentages. Then we have cumulative percentage. Cumulative means it will add up. So this alone is contributing 64.8%. But if you add 64.8 plus 13.9, so these two together will contribute 78.7% issue. So these two together are contributing 78.7. 78.7 plus 10.2. These three together are contributing 88.9% issues. Plus 4.5. These four are contributing 93.4. So eventually it goes on till 100%. So it helps. This is cumulative frequency. The same numbers that you see at the bottom are listed on the top also. This is the cumulative frequency line. Same numbers, which you see here at the bottom, is displayed as a line graph. Now, what is the logic of 80-20? Basically, Pareto chart, the logic is it's stated that if 80% of your issues will come because of 20% reason. Some reasons, some issues may be contributing a lot of issues for you. And there could be a lot of issues which may be happening once or twice or thrice. So it's just about finding the issue which is contributing the maximum number of problems. So 80-20 rule goes by the logic. Technically, you don't have to always go for absolutely 80%. The logic is, I want to see where my maximum defects are coming from. So I clearly see just by looks of it also, that's the maximum defect is coming from these issues. But where if I want to still see which ones are 80% issues, which ones are causing 80%, I clearly know 78.7 is contributed by these two, missing screws and missing clips. So some bit of it, like we add something from leaky gasket, it will become 80% issue. So technically, if I have to solve, I know maximum almost 80%, roughly approximately 80% issues can be solved if I just focus on missing screws and missing clips. That's it. Simple as that. But if I want to get this in a graph, I'll right click in this graph, go to add items and reference line. So I click on reference line. Now it gives me primary scale, which is this count of the issues. Secondary scale talks about the percentages. We talk about 80%, 20%. So 80, so we'll put 80 on the secondary axis. That's it. Click OK. It'll form a line here. Here it bisects. We know this is 78.7. This is where it's 78.7, second north. Just ahead of it will be 80%. This is where 80% of issues are coming from this area. If we want to further kind of get clarity here, I can use this I click here and then kind of mention it like this is the area where it's coming from. 80% issues. I want to highlight that. So that's my like Pareto chart. Again, see a lot of people still argue, and I'm one of them who like sort of thing. This data can be easily interpreted by data. It's not a big deal. It doesn't help me to further get into sort of analysis and this. It's just numbers that I'm rearranging. I could have got this done on an Excel, but yes, images have a lot of like higher retention than the data itself. So yes, sort of it helps. So, but yeah, Pareto chart looks like this. You can get this done on MINITAB. It's very easy to make a Pareto chart on MINITAB. Any questions from the Pareto part of it?
Yeah, no, it's clear.
Okay, perfect. So pretty much moving on to, okay, let me just kind of get rid of this file. Okay. So yeah, left with the scatter plot and control. We'll start with hypothesis and we'll just move on with that. We'll come back and sort of complete the scatter plot today itself. A control chart will happen the last session when we do the control phase. So moving on to the hypothesis part that we have to cover up first. Now, hypothesis, when we say in statistics, there are two types of hypothesis. Hypothesis, literal English meaning is assumption. So we make assumptions. We assume a lot of things. And statistics is all about assumptions. Statistics is all about assuming because you're looking at sample and you're predicting about population. You're assuming it. So in stats, we have two types of hypothesis. One is called null hypothesis and other one is called alternative hypothesis. Alternative hypothesis. Now, symbol for this, I'll sort of write it down, but it's H naught.
H naught, yeah.
HA or H1. Now, the way it looks like is this. So H naught will be sub-zero, H sub-zero, H sub-A or 1. American authors prefer using H1, but again, you should know it's the same thing we're talking about, alternative hypothesis. Now, let's understand what is the basic difference or basic meaning or interpretation of these hypotheses. It is very important for every one of us to get absolute clarity about this because everything going forward, whatever we will be dealing with, it will be all about null and alternative. Every time whenever we talk about in the statistical series that we will be discussing going forward, we should have absolute clarity. So if you don't get it, please ask, because there's no point in going forward if you don't understand this null and alternative, because you will end up talking about this every now and then. So First of all, I'll write down some basic statements. I'll come back and kind of validate, I'll explain about them. So null is a default understanding, or you can say it's a universally accepted truth. I'll come back and explain that. So because it's a universally accepted truth, it does not need to be proven. It's already proven. You don't need to prove a null hypothesis. It's already proven. It's a default understanding. When we talk about null, it always states that there is no relation between two variables. So we talk about, say, there is a factor X and an outcome Y. So we already know Y is my business problem, X are the factors, the root causes. We have collected a lot of possible root causes in the data. We have already collected the data in the measure phase. As per null, there is no relation. X and Y are not correlated. There is no relation between them. Null says no relation. If you are comparing two or more groups, null says they are equal. Null always states status quo. That is equal to. Let's understand so that we can further build on this basic concept. So first of all, like you had this data, the data that you have collected in the measure phase, we have a lot of possible root causes, and we have a business problem that we're trying to figure out. Now, null says there's none of those data, the possible X's are related with Y. There's no relation between them. Say, for example, you're comparing male and female. You have two, like, gender wise. So if you're trying to compare male and female, somebody thinks that male, they are better, and somebody feels that females are better. Well, null will say we're trying to compare their productivity. So null will always say productivity of male is equal to productivity of female. Null will always talk about equal to. They're same, no differences. So bottom line, what it says, there are no differences in the group. Anything that you're comparing, there is no difference between the groups being compared. They are same. There is no difference between them. Like we were comparing, say we have got shifts, like we have morning shift, evening shift, and we have night shift. Null definition will say all shifts are same. So in terms of productivity or whatever, null will always talk about same. There is no difference. You're trying to compare managers, manager 1, manager 2, manager 3. Null says all manager performance, productivity is same. There's no difference in their performance, knowledge, whatever productivity, whatever we're trying to assess, they are same. Null will always talk about equal. Null always comes with equal to sign. Like some example, let's have a look at it. We'll get the clarity here. So say I go and pick up, I like this, one of the favorite things, pretty much that's what I end up using, chocolate. So that's what I love, eating chocolate. So I go to and I purchase, like pick up a chocolate bar, and it's printed on that. It's one of the best chocolates in the market, probably the Belgium chocolate. And it says it is equal to 500 grams. Well, it's printed on it. It's understood it's 500 grams. And I pick up the chocolate bar, I don't doubt it. It's 500 grams. There's no doubt, no confusion. When I look at it, it's a default understanding. I understand it's a universally accepted truth. It doesn't need to be proven again. It's already proven. It's printed. When I look at it, I believe it. Simple as that. There's just no arguments about that. So something which is already proven. Say I have, like we talk about like various car makers. We have got Audi, Ferrari, or whatever, BMW. So probably say BMW comes with an advertisement market that their new car variant will give you 75 kilometers per liter sort of average. Well, that's insane. That's not possible in a car sort of thing, probably as of now. But yeah, probably they must have done something. Well, if the BMW is coming up with certain claims, they must have done something. So I start believing it. These are universally accepted truth. It comes on its own, but practically these are not debatable. We listen to it, we believe it. A lot of factors like this null hypothesis, it's going on since ages. It's a part of our society, it's a part of our culture. We all believe it. Like for example, there's there's a country by like we have by the name of like Australia. I have never been there, but do I believe it? Yes. I have not tested it, but I believe it's there because a lot of people have been there. I've seen a lot of videos and all that. So I've studied in books. Well, I believe it's there. So there's something called Australia and on the world map. Yes, I believe it's there. These are universally accepted truths. For example, again, there's certain more. Probably let's understand. Uh, Up there in the sky, there is something called heaven. And similarly, up there in the sky, there's something called hell. So we do good stuff, we will go to heaven. We don't do good stuff, we'll go to hell. Well, have we seen these hell or heaven, or probably the fairies, fairy tales, whatever we talk about? We haven't seen such thing. But do we believe on this? Like, yeah, since childhood, we grow, and we pretty much have been hearing about all these things. There is something called hell or heaven up there in the sky. We haven't seen it yet. But yes, do we believe it? Yes. It's a part of society, it's part of the culture. We all talk about it. These are understood, proven. You don't need to prove them. People already believe them. But now that's when it brings us to alternative hypothesis. This is probably our generation. I'm not going to believe because you saying so. Well, show me the proof. I need validation. I need proof. Well, well, we talk about, so this is alternative could be, this is called research hypothesis. This is also known as claim. This is also known as challenge. Well, because we are challenging. We are saying, no, Null, you're wrong. Show me the proof. I need a proof. Bottom line, I'm not going to believe because you say so. So I may come back and challenge, say chocolate is less than 500 grams. So I think it when I pick up the bar, chocolate bar, well, I think it's little lighter. It's not 500 grams. I'm doubting. I'm challenging. I'm not saying I'm not agree. I'm not okay with 500 grams. Well, I think it's less than that. Or I might think, oh, no, I think it's little heavier than 500 grams. Or I might just say, no, it's not equal to 500 grams. So alternate hypothesis is a claim or challenge which tries to prove that no, Null, you're wrong. And I might come back and challenge and claim in three different ways. I may say it's less than that, it may say more than that, or I might say it's not equal to. All in all these three cases, I am contradicting equal to, equal to, equal to. Null will come with equal to, and that's what we're trying to prove and claim that no, this is not right. So how do I check it? I'll go and get a weighing scale. I'll check it out whether null is right or alternate is right. Bottom line, I am trying to claim something, and I'll get to know when I do the testing. But the claim can be made these three ways. Alternative can be claimed by proving, well, saying that it's less than that, greater than that, or not equal to. So bottom line we need to understand is we always need to prove alternative hypothesis. You don't need to prove null. Null is already proven. It's already proven. It's a universal truth. We are not even talking and like about proving it. It's done. All we want to prove, because you are the one who's having a problem, right? You are the one who's coming and saying, no, this chocolate is not less than, is not 500 grams. You prove it. Responsibility of proving is yours. Alternate needs to be proven. Null doesn't need to be proven. It's already known to people. It's understood. You are the one who's coming and proving it. So always you need to prove an alternate. Null doesn't need to be proven. Null doesn't need to be proven. It's already proved. While you're trying to do that, that null is wrong, you may get into like different situation. Either you will be successful in proving null as wrong, or that's where I want you all to keep in mind, or you will fail to prove that null is wrong. Now got to keep this basic stuff in mind. Technically, people will, during interviews, people will try to kind of corner or find out the loophole here, the way we present this. Say, you were able to prove that null is wrong. Yes, you checked the weight was less than or more than whatever, you were able to prove it. So null was cancelled. So what we will conclude after this testing is that we reject null because it's proven wrong and accept alternate. So we did the test and we found that it's less than or more than whatever it was. We reject null and we accept alternate. Say you test and you find that it's equal to 500 grams. Now you cannot say you cannot say that null was proven right. It came as 500 grams, but you can't say it's null was proven right because it was already right. You are the one who are trying to prove it wrong. So what you will say instead of this, you never say that this is a wrong statement. What you have to say is we failed to reject null. You were trying to reject null and you failed. Simple as that. Never mention that null was proven right. Either you will be successful in proving it wrong or you will fail in proving it wrong. You cannot say that null was proven right. That's the basic technical part. Yes, this is what you got to keep in mind, because a lot of people during interviews, they will make you say that null was proven right just to kind of like point you down, like ping you down on certain scores. Because you can't say this, because null is already proven. It doesn't need to be proven again. It's already proven. You are the one who are trying to prove it wrong. You will be either successful or you will fail to prove that null is wrong. That's the conclusion of every test. Every test that you will do, you will have two sort of outcome. Either you will be successful in proving that alternate is right, or you will fail to prove that null is wrong. Bottom line, that's how it can happen. Now, that's how we do it. Like, is this basic thing clear to everyone? How do we understand what is null and what is alternate? We look at some examples before we move on. But yes, for now, is it making sense to everyone?
Yeah.
Yes. Can you please explain alternative?
Alternate is okay. Let's have a look at the example, and pretty much that will be the easiest way to understand it. Have a look at this. Okay, this is null and this is alternate, H1. And don't ignore this H2 because we're trying to like have another alternative version. Just let first concentrate on the first one. As a result of employee safety program, there will be no difference in employee injury. This is what we're saying. Probably this is null definition. Alternate says, as a result of employee safety program, there will be a difference in the employee injury. Now, the situation here is probably there are a lot of accidents happening at workplace. So you're concerned with those accidents and you want to convince the management that we must do some sort of training program, employee safety program. If we do this program, people will be more aware, and then there will be lesser accidents and lesser injuries. So we want to develop a relationship that employee safety program is related with the accidents and employee injury. If you do this, there will be lesser injuries. You're trying to prove something, that if you do this, this will happen. You're trying to prove something. Null always says no relation. Employee safety program is a training program. Injury is something else. Why are you trying to compare and bring relationship in two different things? Not correlated, nothing. This is a training, this is injury. Like, why kind of do this mess up here? So that's how null will always try to say that there's no relation. This and this, they're not related. Alternate will always try to develop a relationship, that this will lead to this. For example, somebody has a problem of domestic violence. So what we're trying to counsel and do counseling for the family and say, well, if you take this person to some psychiatrist or do some anger management therapy, well, this person will be able to control his anger, and then there will be lesser domestic violence. So you're trying to develop a relationship between anger management therapy and the violence. Null says, forget about it. There's no relation. One is anger management, another is violence. What are you talking about? This is a therapy. This is the, like, practically there's nothing related in there. Like playing violent video games leads to violent activities. Well, we're trying to develop a relationship. You play violent video games, that will lead to you like a behavior which will be violent in nature. Null says no. There's no relation. One is a game, another is like doing a violent activity. No relation. Null always talks about no relation. Alternate will always try to develop a relationship. So all in all, you got to keep this in mind whenever you have any statement, like all the data that you collected here. Like let's have a look at it. Well, simple understanding. This is the data that we collected. Ticket closure time. We had this X as, this is my Y business problem. So we had an X called ticket handler. We wanted to prove that ticket handler has an impact on ticket closure time. So who is the ticket handlers? We have got multiple: Jaya, Nitin, Ravi, and Vandana. So they're different ticket handlers. We want to prove that ticket handling time is very much impacted by who is handling the ticket. So we want to say that ticket handler has an impact on ticket closure time. Null says no. Everyone is the same. There's no difference. There's no impact of the person who is handling the ticket. Well, probably we want to prove that gender has a role to play, either male or female. Somebody has a impact on ticket closure time. Somebody is very good, somebody is very bad, but there is a role of gender. Null says no. Let's not be gender biased. Male or female, they are same. There's no difference in the ticket handling time. Somebody wants to claim like age group matters, like less than 20, between 20 and 30, and more than 30 years. Well, probably we have different types of age group. Null says be it any age group, the ticket handling time is same. Alternate says no, no, no. Somebody, either younger people are faster or older people are slow, whatever. But bottom line, there is impact of the age group. So null will always talk about no relation, absolutely same. Alternate will always try to prove a point. No, there is impact, there is a relation. Is it okay now?
Yeah.
Okay. Now, pretty much the last example on this null and alternate, and then we will move on to the, move on further. So this is for everyone. See, just take an example. Somebody is caught at a crime site, and this person, there's a lot of people who have seen this person committing the crime. So there are a lot of witness. A, we have witness. B, there was a CCTV footage also. So there is a CCTV camera which has captured the person this particular scene, and the person is seen committing the crime. So number two, there is a CCTV video also. Then the police caught the person red-handed at the crime site. So police caught the person red-handed, and there is a weapon also. So pretty much we have four things. A, we have got the CCTV footage. B, we have witness. C, we have the police caught the person red-handed and with a weapon. So now, in your opinion, when the person is taken to the court, what is the default definition? What is the null definition for the court? Is the person innocent, or is the person criminal in the eyes of court? What is the null definition, default definition? You can use the chat. I'll just stop sharing and I can get back probably to take care of the black box sort of thing. I think it should be fine now. You can use the chat option and let us know, is the person innocent in the eyes of court, or is the person guilty? When this person is taken to the court, is the judge looking at that person as an innocent person or as a guilty person? What is the default definition for the court? Null or what is the null definition? Innocent or guilty? Innocent. How about others? How about others? We've got like two people who have commented. If this person is taken to the court, how is the court looking at this person? Like, is this person innocent as per the court, or is the person guilty?
Say innocent.
Okay, most of us say innocent. Yes.
I'm guilty.
Okay, the correct answer is innocent, and let's understand why. Very simple. Bottom line, the reason why you having a court trial, always, whenever in dilemma, we want to ask a question like, which one is my null statement? Which side is the person innocent, or is the person guilty? Which one is my null statement? Which one is my alternate statement? Always keep this in mind. You always need to prove alternate. The reason why you're having a court trial, because you have to prove in the court that this person has committed a crime. You have to have the witness come and give the testimony. You have to show the CCTV footage. You have to give the show the evidence. Once you have given enough evidence in the court, then the judge will look at all those evidence. In the light of those evidence, then the judge will say, no, no, we have enough evidence to prove that this person has committed a crime. Hence, proven the person has committed a crime. The things that you need to prove are alternate. You don't need to prove null. Null, the person is as innocent as the judge himself. You don't need to, this person does not have to say even a single word to say that I am innocent. You are the one who has a problem. You want to prove that this person has committed a crime. This person is a criminal. Prove it. Your responsibility, not mine. So you take me to court and you say that you have committed a crime. It's your responsibility to prove it. So the reason why you need to prove something, that would be alternate. Null definition will be innocent. Simple as that. Whenever in dilemma, ask a question from yourself, what are you trying to prove? If you're trying to prove something, that's an alternate statement. Here, what are we trying to do? We're trying to prove that ticket handler has an impact, gender has an impact, age group has an impact. The reason why, because you did the brainstorming session, you believe that these are the reasons why the ticket closure time may be impacted. So these are possible reasons. You believe in them. You want to prove that these are root causes. But null definition will be this has no relation, this has no relation, this has no relation. No X is related with Y. Alternate will always try to prove a point. This is related this is impacting this is impacting this. Null will always say no relation. Alternate will always try to prove there is a relation. I hope that is clear to everyone now. Null and alternate. Is that okay? Okay, all right. Now coming back to now in case of a court trial, we had the evidences. In case of a statistical test, when we're dealing with data, what is the evidence here? The evidence we have here is p-value. We remember we had a p-value when we did Anderson-Darling normality test. When we did a normality test and we got a p-value, looking at p-value, we decided the data is normal or data is non-normal. So this is the evidence which we use to check and confirm whether null statement is right or alternate statement is right. So p-value is the indicator or the judgment through which we will understand which statement is the right statement. Is it a root cause? Is it impacting the business problem or not? Is it null or is it alternate? So p-value is what we will be dealing with. Now, what is this p-value? It is the chance of making an incorrect decision. It's the other way around. What is the probability? What is the probability of making an error? What is the likelihood that you will end up making an error is p-value. We'll understand it other way around. When we look at example, we'll understand it automatically. Like for now, just keep this definition as it is right here, but we'll be able to make sense out of it when we look at the basic example. Now, if you all remember, we did testing using MINITAB or anything else. We did testing at 95% confidence level. Everything gets tested default at 95% confidence. What is this 95% confidence level means? That you are 95% sure that your predictions, your calculations, whatever you want to assume or predict, that is going to be correct. So 95% we are confident. 5% chance is there which says that you can be wrong. There's a 5% chance that you will be wrong. 95% of the time, yes, you will be right. 5% chance you will make mistakes. Yes, that is this risk we call as alpha risk. Now, every null definition is said to have this 95% confidence and 5% risk, which is fixed and you don't. So if you believe the null statement, there's a 5% chance that you will be wrong. What is the probability of you making a wrong decision if you stick with null? If you believe null, your probability of making a wrong judgment is 5%. That you can be wrong, 5%. That's the maximum risk in your null statement, which says there is no relation, everything is equal, all that statement that we talked about. So when we say there is no difference, there is no relation. If you believe on this statement, this data that you've collected, if you want to say ticket handler has no impact, gender has no impact, the age group has no impact, all these statements, which are null statements, they all have 5% risk. If you continue with believing these statements, there is a 5% chance or 5% risk that you can be wrong. Fixed default. Now, the only question is, you are coming and claiming now. You are claiming within your alternative statement. You have a new statement and you coming and claiming, no, 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 this null is wrong. You want to come and claim that this null is wrong statement. I believe based on my experience that ticket handler has an impact, gender has an impact. You want to claim, you want to prove that no, null is wrong. There is impact. They definitely impact the customer satisfaction score, does definitely impacts the ticket closure time. The background of the person definitely impacts the ticket closure time. A lot of factors. You want to prove that null, you're wrong. So when you're doing this, all I want to know, how much is the risk? In your claim, whatever statement that you're making, how much is the risk in the alternate statement? You know what is the risk in null. How much is the risk in your alternate statement? For example, let's take an example. You got in alternate statement, you are able to perform some test and you find that the risk in your alternative statement is 9%. This is 9%. Which one would you go with? Are you going to go with null statement or are you going to go with alternate? Which one is going to be your verdict? Are you going to go with null, which is 5% risk, or are you going to go with alternate statement, which has 9% risk?
I'll go with null.
Oh,
Null, definitely yes. Why would you go with more risk? When you have 5% risk in null statement, if you believe that there's no difference, there is a chance that you will be wrong, but only 5%. But if you believe there is a relation, there is an impact, and there is a 9% risk in that, why would I go with 9% when I have 5%? I would not go with higher risk. So I'll say we failed to reject null. So we'll continue with null. Null is a better statement. Null is better statement because 9% risk of alternate is very high. 5% of null is good for me. So I'll go with null. Continue. We failed. We wanted to reject null, but we failed. Say we perform a test and we get a risk of alternate as 2%. Now, which one would you go with? Null or alternate?
Alternate.
Alternate. So we'll say we reject null and accept alternate. Why would I go with higher risk? There's a better statement, 5% risk. Why would I take that when I have 2%? This is more like, this is better statement. I will reject. So I will reject null and I'll accept alternate. Let's take some more examples so that we understand and this basic logic behind it. Say we have something like this. Now this is about 6.5%. How much, which one would you go with? Null or alternate?
Alternate.
Null or alternate? This is 6.5%.
Alternate. No, null. Still go with null.
Still go with null because this is
Yeah.
5%. This is 6.5%. This is more. Is this okay? This is we still higher. So we fail to reject null because null has 5% risk. This has 6.5% risk. This is more. I would not reject null because this has got lesser risk. This is more. These are all risk of alternate that we're looking at. What if we get a risk of 0.04? Which one would you go with, null or alternate?
Alternate.
So we'll reject the null and accept the alternate. We will not go with higher risk. What if you get a risk of 5%? Now, think about it. Null has 5% risk, alternate has 5% risk. Both has same risk. Which one did you go with, null or alternate?
Null.
Null.
I'll go with alternate.
We will still go with null. And let's understand the reason why. See, null is a proven truth, validated. Everyone understands and believes it. You are the one who's trying to prove yourself. You must be better. You have to be better than me. Well, people believe null statement. Why would I change myself? You have a 5% risk. I have 5% risk. Why would I change myself? You have to prove me wrong. When would you prove me wrong? When you get lesser risk than me. So till the time it's less than, if it's less than 0.05, then we will say we reject null and we accept alternate. Every time we go for less than 5%, that's when we reject the null statement and we say alternate is a better statement. This is a, and what are these risk of alternate that we've been trying to find out? This is nothing other than the p-value. P-value tells you the risk of going with alternate. Null risk you already know. Only the thing you want to understand, what is the risk of alternate? This is default fixed. Only the thing that you want to compare and understand, which one is the risk of alternate. That's it. Simple as that. And if you go back and like in this sheet, let me just randomly create some data values. Let's understand. So this is null risk, and here let's have an alternate risk. So which is the p, here the p-value. P-value tells you what's the risk of. So this is fixed, 5%, no changes here, 5%, which is fixed. So all these excess, when we perform some test, we'll understand what the tests are. Different tests will be applied. But yes, for now, we try to understand when we do the testing, we will get these, some p-value. How do we understand which one is the root cause, which one is not? So I'm randomly putting some values here. Please help me understand whether you will go, which one would you go with? Randomly putting some values, so this is not the real ones. We'll understand what the real ones are here. We'll perform the test, we'll get to know the real values. For now, we're just kind of going ahead. Doing it on MINITAB will barely take any time, like, so let's just, but yeah, whatever test we will be doing, we must know what are, how to read and interpret whether it's a root cause, not a root cause. Okay. Some random values, but just a final count so that we understand the basic difference here. So that's the, these are the p-values. We performed some test, we got to know what's the p-value here. Which one would you go with, null or alternate?
Alternate.
Everyone is okay with the alternate?
Yes.
Okay, so because null has more risk, so we will reject null. We'll say, no, null, you're wrong. You're 5% risk. I will go with alternate. So alternate, this is a root cause. So hence we would have a statistical validation which confirms that ticket handler is a root cause. It is impacting your ticket closure time. It's not my gut feeling. We have a statistical proof which confirms that yes, ticket handler is a root cause. We reject null. We confirm that ticket handler is impacting your ticket closure time. So this becomes my root cause. So let's kind of change this to green. Which one would this be, like null or alternate?
Null.
Null.
Technically null, yes. This one?
Null.
Null.
This one?
Null.
Null.
This one?
Null.
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 The next one?
Alternate.
Alternative.
Perfect, perfect. We would reject null and say alternate is better. So number of follow-ups is definitely impacting your ticket closure time. This one?
Null.
Null. Null.
I guess we got it correct. Now let's kind of get in here. This one?
Null.
Null.
This
Alternate.
alternative, and this one?
Alternate.
Alternate.
Perfect. So we got it correct. So this is what we need to. So bottom line, there will be different tests. We will learn about them. Whenever we perform a test, every time we will get a p-value. All in all, we need to understand when we perform a test, looking at p-value, are you going to go with null? Are you going to go with the alternative? If you want to summarize this, very simple. And if you kind of look at some YouTube videos, you will see this people saying this when bottom line, we're summarizing it. If p-value is less than 0.05, you will go with alternate. This is what you will go with. If your p-value is equal or more than 0.05, you will go continue with null. That's your crux of whatever we have discussed so far. This is the crux of every test that you will be doing. Every test, you just need to keep this basic fundamental in mind. You will not go wrong with your statistical test. And the slogan which you will generally hear people talking about in YouTube videos is that if P is low, null must go. That means alternate will come. If P is high, null must fly. So null will continue. So sort of if P is low, when P is low, null must go and alternate will come in. If P is high, then null must fly. So that's how people generally use a lot of slogans to remember this. So that's for the null and alternative hypothesis. Now, before we get down to the statistical testing part of it, we have one more sort of theory sort of thing to kind of cover up, and then we will move on to the test. Now, while we do this null and alternative hypothesis testing, we get to perform some tests, we get to see a null, we get to see an alternate. We decide that there are something called types of error. We can make some mistakes. While we are dealing with statistical test, we can make some error. The errors will be type 1 error. This is also known as alpha error. This is also known as innocent punished situation. Similarly, we have type 2 error also. This is known as beta error. This is also known as guilty released situation. So recruiters could ask you questions in a different way. What is an alpha error? What kind of error has been committed if we punish an innocent? What kind of error we have committed when we have released a guilty person in a court? If a guilty person is released because of lack of evidence, pretty much what error has been committed. So this is what we should know, the different names of the same thing. Synonyms we should remember because people do ask these questions, but these errors have gone down drastically, and we'll know when these errors can happen, what is the reason. But what is the error? Let's understand. If we end up proving null as alternative, you have committed a type 1 error. And this is the other way around. If we end up proving alternate as null, you have committed a type 2 error. Null means there is no relation, but you end up proving that there is a relation. You have made a mistake, right? It's an error that has been made. Like in a court, the definition is the person is innocent, but because of wrong evidences, you people coming and giving wrong testimony and all that, wrong evidences, you end up punishing the innocent person. That's an error. That's a mistake done by the court. That's a type 1 error. So when you end up proving null as alternate, that will be a type 1 error. Somebody who's a guilty in the court of law, people don't come and give the testimony, lack of evidence, the person is released. The error has been made, mistake has been made. That is a type 2 error. In a statistical world, what we will do, a factor which has no impact on your business problem, you end up proving that it's a root cause. You will work on it, you will not see any result because it's not related, but you made a mistake of proving it as a root cause where it was not. You will see no improvement in your business problem. When you, or for that matter, if you have committed a type 2 error, a real root cause which was impacting your business, you would have marked as null. That means no relation. You will not even work on it. You'll discard it. And because you don't work on it, you don't see an improvement in your business problem. Both these errors can happen and will happen because of two reasons primarily. One is insufficient sample size. Again, going back to your measure phase and your incorrect sampling methodology. This is like predicting or basically concluding too early. So you collect the data, insufficient sample, and you start you've not done your maths, you've not done your statistical testing and analyzing what is the right sample size, and you end up using a small sample and you take a decision. That will end up you getting into any of these error. Or if you have collected a biased sample, an incorrect sample, then again, you will end up making some wrong assumptions. So again, this goes back to your measure phase. Should you do this correctly, you will not come across these issues. About a decade ago, when we did not have good sampling methodologies, when people were still using traditional methods of collecting sample size, people were making tons of such errors. But now, because you know what is sample size calculation formula and you know the good sampling methodologies, these errors have gone down drastically. Yes, but you can never say that we are always free from this. No, the moment you end up making any of these mistakes, you will end up making these errors. That's how you got to keep this bottom line, this basic thing in mind, that these errors are prone to us because of the mistakes or error we might do in the measure phase. But all in all, if you keep these basic stuff in mind, the sample size calculation and the methodology, and you know the good sampling methodologies we have, we can kind of keep ourselves away from these errors. I hope we are good with this types of error.
Yeah, that's good.
Yeah.
All right.
Yeah.
Coming to the final hypothesis testing part of it, the test that we will be using, that we need to kind of learn. So whenever you start with your data analysis, like that's what we'll be starting from scratch back again, including the normality testing. We learn about all these testing part of it. So let me get rid of this chat now. First thing first, whenever you have data like this, you collected data, your data is ready for the end of measure phase. Now you want to start with your analyze, like statistical testing. What you will always do first, check the normality. Always. How do you check normality? Anderson, Darling normality test. Now, what is my null definition? We'll go back to a null and alternate for everything now. Null and alternate. This is my default definition with respect to data. Always, data is always normal. These are standard definitions as per stats. Data is always normal, default definition. Alternate will always have a problem. Data is non-normal. That's the standard default definition with respect to data normality. Data is always normal. Now, we would like to know, is my data normal or data non-normal? The null definition, we know what is null and we know what is alternate. So let's get the data here. Let me copy paste the entire data and paste it on MINITAB. Let's go step by step. The way we will do it in real world. We have the data, we get the measure phase done. First thing, let's complete the normality. So stats, basic statistics, and say normality test here, or you can do a graphical summary. Both ways you can get your normality done. Let's go to normality test. Ticket handling time. Test Anderson Darling. Simple. Let's click OK. You get your p-value. Now, don't look at that logic. Remember the logic that we used. P-value 0.587. Go back to this one. When we did the test, the p-value we got was 0.587. Now, which one would you go with, null or alternate? P-value 0.587. Does it tell you to go with null or alternate?
No.
Remember the same logic. Okay, let me just copy
Null.
paste it here.
Yeah, null. Always.
Yes. Now everything will relate with this. Just keep this in mind. This is p-value. When it is less than 0.05, then alternate. This one is null. This one is null. Null means data is normal. So this data is normal. Is this making sense? Null and alternate?
Yes.
Let's do another, just for an argument's sake. Let me do the testing for CSAT score, normality test, just to check. Same logic, normality test. I want to test CSAT score. This one is coming as less than 0.005. This is p-value. P-value, if it's coming as less than 0.
Normal value, normal data.
Absolutely. This one falls into the alternative zone. So this one confirms this is alternate, and alternate says data is non-normal. Alternate means data is non-normal. Now, I hope this one is good. We can move ahead with the normality part.
Yeah.
Okay, let's move on to the next thing then. Once you've checked your normality, the next step, which you should always do, is check for randomness. And we'll understand what is randomness, or people also call it as check for stability also. Is your data stable or not? We'll understand what is randomness. how do we do it? The name of the test is run chart. So what is the null and alternate definition? Let's first write it down, then we'll elaborate on that. Same, similar, null always talks about good stuff. Data is always random. Alternate says no, data is non-random. Alternate always has a problem. We always want to claim and prove something. So we'll perform a test, run chart, and we'll get to know, is the data random or data non-random? Is the null right or alternate right? Looking at p-value. So going back to this, ticket closure time, let's do the run chart. Start, quality tools, and the first one is run chart. Click on the run chart. Ticket closure time. I wanted to select ticket closure time. Subgroup size 1, single column 1. That's it. Click OK. That's how your run chart looks like. Let's have a look at it. Now, what do we read in this run chart? How do we understand the randomness part of it? Now look at this. You can see p-value for clustering, p-value for mixture, p-value for trend, p-value for oscillation. So there's actually 4 p-values here. So there are p-value for clustering, mixture, trend, and oscillation. So going back to the Excel, let's make the notations first. What is randomness? If data has no evident patterns, that is, it's free from any pattern, it is random. Even if it has one pattern, also it will become non-random. What are these patterns? There can be 4 types of patterns: cluster, oscillation, mixture, and trend. If any of these p-values is less than 0.05, it confirms presence of that pattern in the data, which makes it non-random. Let's understand what it. So any data can have 4 types of patterns. If the data has no pattern, free from patterns, it is random data. If it has even a single pattern, it will become a non-random. Now, what these patterns are? 4 types of patterns. We have seen this: cluster, mixture, trend, and oscillation. If any of these p-values if it is less than 0.05, that means the data has become non-random because of that pattern. So is this less than 0.05? No. Is this? No. Is this? No. Is this? No.
No.
None of these p-values are less than 0.05. This data is a random data. This is free from all these patterns. We do not have any of these patterns in the data. But let's have a look at another example. Same CSAT. Let's look at the CSAT thing. Do we understand what's a random and what is non-random? Just by looks of it. Clustering. This is less than 0.05. So this has made the data non-random. So it confirms there is a clustering issue in the data. The data is clustered in this. This is not. There's a trend issue in the data also. So there are 2 types of patterns. There's a clustering pattern and there is a trend pattern in the data, which is making it non-random there. So there are 2 patterns, which is making it non-random. So bottom line, when we look at the p-value, these p-values, we look for p-values, and if any pattern is less than 0.05, which will make it non-random. So if you're getting a p-value, which confirm, if you say you're getting a p-value, which is anything which is less than 0.05, it will make it non-random. If all the p-values are more than 0.05 or equal, you will get this random. Is this clear?
Yes.
Okay.
Yes,
Now,
yes.
a basic question. Now, we checked for normality. Why? Because we wanted to know, is the data normal or non-normal? Why we wanted to know normal or non-normal? Because normal data, we look at mean, and non-normal, we look at median. But what is the purpose of this random or non-random? Like, we understand normal means we look at mean, non-normal we look at median. Randomness. Randomness, the purpose of randomness, one of the statistical test, which is ANOVA, can only be done on random data. If data is non-random, then instead of ANOVA, ANOVA, we will use Kruskal-Wallis test. We'll look at it. We'll make a chart for that. But just to kind of give you an idea, the purpose of doing a randomness test is we get to know is if the data is random, then only we can use the ANOVA test. If it is applicable, we want to do ANOVA test. The data must be random. So we must have checked the data is random or not. If the data is non-random, then instead of ANOVA, you have to do a Kruskal-Wallis test. We'll look at that test. Bottom line, that's the purpose. Now, the third thing is now we start with the testing. The statistical testing is the hypothesis testing part of that we are going to deal with. So this data that we have, we will be doing hypothesis testing with this. First thing first, so this is my normal Y, which is here that I'm trying to test data, the normal Y, and I will have X in the data. So X, which is possible X is X, which is numerical, and X, which is categorical. Let's first of all understand what is this numerical and categorical part. So in my data sheet, if I look at this data, this is my normal Y that we have tested. The data, the X's that I have, all these X's, ticket handler, gender, either there will be a number or it will be a text. See, when you have the number based, it becomes T, alphanumeric T, numbers, all numbers, it just remains C6, all numbers, C7. So if the data is numerical, which will be like this, it is numerical X. If the data is text, it will be a categorical one. If you go back and look into Excel, let's kind of check this out. So let's get rid of this top rows first. Okay, so this one is my categorical X. I have 4 different categories. Jaya, data for Jaya, Nitin, Ravi, and Vandana. This one is gender. So I have male data, females data. I have 4 different age groups. These are categories, groups. Group, category. This is number, pure numbers. Data will either be a number or a text. So in our case, MINITAB automatically understands data as a number or a text. So if we are dealing with data, you will have some data which will be numerical X's, some data which will be categorical X's, which is text-based X's. So if you're dealing with numerical X's, you want to check whether this X has an impact with Y. Is this X root cause or not? The name of the test is correlation. And you always use the graphical 7 QC tool, scatter plot, that we talked about. Scatter plot that we had to cover up here. So correlation with scatter plot will be used. So correlation plus scatter plot goes in for testing numerical X's. Scatter plot is the graphical test. Correlation is the statistical test. Coming to the X categories, which are when they're categories, then they will be further categorized as 2 groups and 2 plus groups. Let's understand first what's that 2 groups and 2 plus. But let me write down the name of the test and then we'll go back and check this out. If you have 2 groups that you're comparing, like male, female, morning shift, evening shift, the 2 groups only. If you're comparing, the name of the test is 2 sample T test. That's what you have to do. And for 2 plus groups, you have to do one-way ANOVA. When you're comparing more than 2 groups, like you're comparing morning, evening, and night shift, 3 groups. You're comparing manager 1, 2, 3, 4. So more than 2 groups will be one-way ANOVA. If data Y is random. In case it's non-random, then use Kruskal-Wallis test. Let's have a look at this. Which test will be used for in which case? First thing first, this is my Y. That is what I'm checking. But now I want to check whether ticket handler has an impact. Is it a root cause or not? Which test will I do? Anyone wants to pitch in?
What's the question again?
Ticket handler, I want to check whether ticket handler has an impact on ticket closure time. Which test will I pick up from that list? I'm sorry?
T-test.
Not the t-test.
One-way ANOVA.
One way ANOVA. Going back to it, so let's quickly understand.
Categorical
2 plus ANOVA. When you have more than 2 groups, then you do ANOVA. 2 groups, you do 2 sample T. Let's go back to this Excel back again. So how many groups are there? Jaya, Nitin, Ravi, and Vandana. So we have data for Jaya, we have data for Nitin, we have data for Ravi, we have data for Vandana. So we have 4 groups here. So more than 2 groups, ANOVA. ANOVA will be used when I want to test whether ticket handler is the root cause. I'll use one-way ANOVA test. Let's check the second one. Which test will I use for this one?
T-test.
2 sample t-test. Perfect. Yes. Because I have data for male, I have data for female. Only 2 groups. I want to compare whether male and female they are same or not, or they are different. So 2 groups only will be doing a 2 sample t-test. Let's have a look at this one. Ticket handler age group. Which test will I be using here?
One-way ANOVA.
Perfect.
one-way ANOVA.
Perfect. There are more than 2 groups. There are 3 groups actually. So yes, one-way ANOVA is the right test here. Let's look at this. Which one will I use here?
T-test.
Perfect. 2 sample t-test. Which one will I be using here?
One-way ANOVA.
No.
No, it's a numerical.
Numerical.
Yes,
Yeah.
yes.
It's numerical. The other one.
Correlation, yes.
Correlation, yeah.
Yes.
Scatter plot.
Correlation or scatter.
Perfect. Same numbers.
Yes,
Yeah.
correlation.
How about this one?
One-way ANOVA.
One-way. No.
Perfect. Let's go
ANOVA.
and let's check some more. Shift.
T-test.
Perfect.
Yeah.
How about this one?
One-way
One-way
ANOVA.
ANOVA.
One-way ANOVA.
Perfect. This one.
T-test.
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 Okay. How about this one?
One-way
One-way
ANOVA.
One-way
ANOVA.
ANOVA.
If my data is non-random, then which test will I be using here? If my
Corpus.
Crystal Wallace.
Bruce
Yes,
Willis.
yes. Perfect.
Bruce Willis.
Crystal Wallace. Perfect. How about this one?
One-way
One-way
ANOVA.
ANOVA.
Perfect. Yeah. How about this one?
T-test.
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 Perfect. Trust, knowing which test needs to be done is more important because doing it on MINITAB will barely take 2 clicks and we will be done. So it's as simple as that. But yes, knowing it is more important. Otherwise, we will end up doing a wrong test, which should not have been used. Having said that, let me just add in. So here we have graph as scatter plot. The graph used.
Question.
Yes, please.
So when do we use the two-way ANOVA?
No, we in case of a 6 Sigma project, we don't use 2-way ANOVA. That is when you go ahead and use, see, when we have 2 different metrics to compare. Here in a 6 Sigma project, we only have a single metric that we kind of look into. Then we get into the statistical testing, like when you go into deep statistics, yes. Then we have 2-way ANOVA, we have MANOVA as an all, like we get into all that. But yes, in a 6 Sigma projects, we end up only kind of dealing with a single metric, which is a single Y. We use 1-way ANOVA.
Okay, thank you.
Here, the name of the graphical plots that we'll use is box plots. We all know box plots. So test and the graphical plot, test and the graphical plot, test and the graphical plot, which is scatter plot. So first we will start with the 2 sample t-test, understand how to do this, interpret this, move on to then ANOVA, and finally the correlation scatter plot. So let's start with 2 sample t. I'll do one of it, and I hope everyone has this access. So we'll give a short gap in between for you to perform the test also. First, let's do a 2 sample t, which will be 2 groups. So in our data, the 2 group is say gender, male and female. So what is my null hypothesis here? My null hypothesis says male ticket closure time is same as female ticket closure time. The average of male and average of female, they are same. Alternate says no, there is a difference. Male or female, they are significantly different. Let's see whether it's different or not. So gender, we would like to test. So I go to stat, I go to basic statistics, and here we go down till 2 sample t. It also says, determine whether the mean differs significantly between 2 groups. Click on this. Samples, when you click in this box, it will give you samples. Samples will contain your Y, the business problem, which is ticket closure time. Select this ticket closure time. Sample ID will contain your X, which is gender of the ticket handler. put in the gender. So Y will come on the top, X will come at the bottom. That's it. Ticket closure time versus gender. Click OK. Now your testing is done. Let's understand to interpret this. We always start with the p-value first. What does this p-value tell you? Null or alternate?
It's less than 0.05, so that's alternate.
Perfect.
Alternate.
It's alternate. Yes, it's less than 0.05. Thank you. That's the logic we have to always keep in mind. Is it less or not? It is less. Yes, it is alternate. So yes, it's a root cause, validated root cause. We have a statistical result, statistical evidence, which confirms that gender of the ticket handler is a root cause. I'm not being gender biased, but there is a relation here and we have been able to prove it. So male or female, somebody is doing a terrible or a terrific job, but yes, there is a huge difference between them. So look at p-value. Yes. Now let's deep dive and understand what's wrong and what's good and what's bad. Now, few questions. This is where we would like to look at. Female, there are 80 values in this rate in the sheet. Male has 101 values, like the data points. Female 80 data points has an average of 17.24 minutes. Male data points has an average of 19.75 minutes. Now, few questions that we need to understand, because I could have done this average even on Excel. I could have calculated the average. We all know how to calculate average. Put down a filter, we could have calculated the average. This could have been done on Excel also. But what we're trying to understand here is few questions. How do we read and interpret? If you want to ask this question from yourself, how do I read this? First question, do I see, sort of just to get a clarity, you don't have to write this, but just to get a clarity, how do I read and interpret? Do I see a difference in the group averages? Obviously, do I see? Yes, I do see a difference in the group averages. This is 17.24 minutes. Females are taking lesser time. Lesser the better. Females are doing a great job. Well, I won't say great job right now because I don't know it's great or not, but yes, they are taking lesser time. Male 19.75 minutes, which is more time. So do I see a difference in the group averages of male versus female? The answer is yes.
Yes.
Is that a large enough? So now the few questions, is that a large enough difference between the groups to claim that they are statistically different? And technically they are performing at an absolute different level. Is it a large enough difference? We can say male and female, they're absolutely different, like 2 poles apart. Is that large enough difference? That
Yes.
question, the answer of that question needs to be understood. Second, even if and if that's the question, so that's the question. And to continue with this, and if we change the sample, because we would have picked up this sample from the process, if we change the sample, like we increase the sample or we reduce the sample or we pick up a new sample from the process, is this difference still going to be a large and statistically significant differences? And this is just not about 2 sample T, every test. That's the logic, and the concept needs to be understood. These are the questions we're asking in our mind. A, do I see the difference? Yes. Is that a large enough difference that we can say they are absolutely different, 2 poles apart? And if we change the sample, because we know that average is like, obviously the 80 data values, this is 101. If we add more sample, obviously the averages will change. If we reduce the values, if we pick up a different sample, obviously the values will change. The means will not be same. This is for this 80 data points. This is for 101 data points. What if we change the sample? The average will change. But the question is, if we change the samples also, if we increase sample, reduce sample, pick up a new sample, are you still going to see the difference? Are these permanent differences? Are these differences permanent, or basically real differences and not by chance? The answer to all those questions is your p-value. Yes. We look at the p-value. If p-value says it's less than 0.05, now looking at the sample differences, I am concluding about the entire population. Look at the symbol mu, mu. These symbols is for population mean. You're talking about there is a process from which you picked up a sample. You understood the descriptive statistics. Now this is coming to the inferential part. Looking at the different descriptive statistics, you're predicting about the entire process. Even do I see a difference? Yes. Is it a large enough difference? If I change the sample, will you still see this large difference? The answer to every question is yes. These are real differences and large differences, and females are doing a better job in that process. Not in this sample, in the entire process, females are doing a great job. And even if I pick a different sample, I will still see similar differences there. So that's how we read and interpret this information. I hope we got this correct. It's clear to everyone.
How can we ensure that if we pick different samples, then it did not affect on our mean and p-values?
So sampling process, that's for sampling methodology. Sample should be a true representative of the population. That everything goes back to your measure phase. And if it doesn't, like, see, bottom line, your values will change. So it will reciprocate accordingly. The differences will still be there. You will see this is not by chance. So if, because see, you're picking up a sample, what if you pick up a new sample? The interpretation of the entire process is not going to change. Statistics is all about looking at sample and predicting about the entire process. And where is the base coming from? Your measure phase, sampling process. You picked up a right method. The sample should be the way you're picking sample, the process of picking sample has to be authentic enough that you picked up a true representative of the population. When you're picking up true representative of population, whether you pick sample from this first time, second time, third time, it should give you similar information. I hope that makes sense. The
Yeah,
essence is
thank
your
you.
measure phase. The base is your measure phase. You go wrong in measure, everything will go wrong. So that's how we really want you to kind of like definitely keep this in mind. This is the base of everything. Keeping in mind you've done correct thing in your measure, you will not face. Bottom line, get your rational subgrouping and your what do you call this one? The other one, like the population based one. Um, I'm sorry, I'm like not able to recall the name. The you, which one can you please sort of help me out, Will? Just not able to get the name of stratified random sampling. So just get your clubbing done for stratified random sampling and rational subgrouping. You will have a good sampling process. Ideally, you should pick up samples from every area. You should not overemphasize one area and ignore another. Simple as that. That's how it works. Now, let me pick up another example from two sample T and then probably move on to the another one. Stats, basic statistics, and two sample T. So this is my Y, and I'll change my X. Say I'll change this to shift. Like I've got two shifts only, morning and night. Well, null says be it morning shift time or evening shift time doesn't change. Well, practically average is same. Alternate says no. There is a huge difference in the productivity. What does it tell me? P-value.
It's greater than
higher.
0.05. It's null.
Null, no differences. They're same. Well, if bottom line, do I see a difference? Yes. Is it? Can I call it as large difference?
No,
And
it's
all
not
those questions
significant.
is all those
No.
questions. The answer looking at p-value, no. The differences you see could be by matter of chance. These are not real differences. If you change samples, you'll still see they are like almost the same. There's not enough differences. Sorry, we wanted to reject null. We could not. We failed to reject null here in this case. The interpretation, the conclusion will be we failed to reject null. Not that null was proven right. We failed to reject null. So I hope two sample T is okay with everyone.
Yeah.
Yeah, it's okay.
Okay. So it's almost like 3:50, like Indian time. Shall we take a quick 10 minutes break and shall we be back? Because ANOVA and correlation will take some time. So we can come back and go for final 1 hour after that.
Sure,
Okay.
sure.
10 minutes from now, whatever time zone we are in, 10 minutes. Let's be back.
Okay.
I hope everyone is back from the break.
Yeah.
Yes.
All right. So let's get started with the other test, which is for the two groups. When we do one-way ANOVA. So we have data for one-way ANOVA where we have more than two groups, like this ticket handler. Even in this case, the same logic applies. The null definition says the ticket handler of Jaya is same as Nitin, is same as Ravi and Vandana. So technically, it doesn't matter who is handling the ticket. The ticket closure time is going to be same. Alternate says no. Somebody in this group is exceedingly well, and somebody is really bad. But yes, there is a huge difference in performance levels. We would like to check whether it's a root cause or not. So we have more than two groups. We do ANOVA. So we go down to start ANOVA, and we do one-way ANOVA. You click one way. Response is my Y and factor is my X. So I click here, response, ticket closure time, factor, ticket handler. Now in ANOVA, we do an extra bit of thing, which we click on comparison, and we select this two key, and we'll see it's a very meaningful information it gives. We select this two key comparison, click OK, and that's it. We click OK. Now let's have a look at the test results. Null hypothesis, all means are equal. Alternate says no, not all of them are equal. They are different. Four groups. We are comparing four groups, which is Jaya, Nitin, Ravi, and Vandana. The ticket handler p-value, it is less than 0.05. Hence, it's a root cause. There is a statistical relationship between the ticket handler and the ticket closure time. So there's enough statistical evidence for us to reject the null hypothesis and confirm, yes, the ticket handler does impact the ticket closure time. Now, let's see who is good and who's bad. In the last case, we saw females were good, male were not doing that good. Let's have a look at this particular data. Jaya has 22 data points in this data. She has an average of 19.19 minutes, and it's at 95% confidence. We can say that she takes about 17.7 minutes to 20.6 minutes to close an IT ticket. That's a ticket closure range for her. Nitin has 56 samples with an average of 20.6. His range is 19.7 till 21.5. Ravi has 45 data points with an average of 18.6, and he ranges between 17.6 till 19.6. Vandana has 58 data points with an average of 16.5, and her range is 15.5 till 17.4. If we look at Vandana's range, she ends at 17.4, and these guys don't even start at 17.4. She is a role model. She is doing exceedingly well from the rest of the group. There's nowhere, they are not nowhere in close to what she is doing. 17.6, 19.7, 17.7. This is where they start. She ends at 17.4. So she is probably practically my role model, who is doing phenomenal as compared to rest of the group. And that is the reason why we're getting an alternate. Having said that, even if we remove Vandana from the data, still we would get an alternate. Why? Because Ravi ends at 19.6 and Nitin starts at 19.7. So there's no overlap. There's no overlapping between them. So pretty much this person is not like, this is, they're like absolutely two different groups. One group which is performing at a different level, another group which is performing at, and this one is absolutely like, even if we have any group which is not overlapping, you will see an alternate. Like if, and the easiest way to read and understand this is using the two key, which we clicked on. Have a look, like read this one. Means that do not share a letter are significantly different. So what it does, it gives you an alphabet to every group. So it has given an alphabet A to Nitin. The data of Nitin has been put into a group called A. Jaya has some features. Jaya's data has some feature of A. She has been given an alphabet A, and she has certain other data which is not like A. It's been categorized as B. Ravi has all the features of B. So Ravi like Jaya has both features of Nitin as well as Ravi, but Nitin and Ravi, they do not share anything in common. This data is significantly different from this data. And Vandana, she's league apart, absolutely different from everyone. So that's what it says, that which do not share letter. When there is any other letter, bottom line, they are significantly different, statistically significantly different from each other. So Vandana, definitely yes. But even if Vandana would not have been there, Nitin and Ravi, they are significantly different. So even if we remove Vandana's data, still we would have got an alternate that it's a root cause. Is that making sense?
Yeah, yeah.
Okay, okay. Let's have a look at another test here for stats, ANOVA, one way. Remove this one. Let's say qualification. We have multiple levels here also. Same comparison is already checked here, to key, and click OK. Have a look at this p-value for, oh look, forget about this one. Yeah, p-value. This is null. This is null. And if we look at, let's look at Tuki, everything is clubbed into one group, same. There is no difference in the groups. When we see a difference in the groups, we will see a different letter. This is null. Null will always have all AAA. Whenever you see a different letter, bottom line, you have two different groups, and you'll always see an alternate here. The Tuki gets you the clarity. There is almost like they are kind of overlapping each other. There's no difference, like they are like, there's some thing which is kind of being shared between them. Let's have a look at something else in case we want to compare. Say we have different managers. Let's see the managers. Okay, let's delete this. Managers by manager. Let's see if manager wise there's a performance differences. No, pretty much not. Null. I hope we are good with ANOVA, everyone.
Yeah.
Okay. Having said that, keep this in mind. If you remember, like we said, that if the data is non-random, we know how to check for randomness. If the data is non-random, so whenever we decided to do ANOVA, instead of ANOVA, we will be doing Kruskal-Wallis test. Where do we find the Kruskal-Wallis? Stat, non-parametric. And here in the non-parametric, we will see Kruskal-Wallis. Kruskal-Wallis. Everything that we were comparing was comparing averages. This one will compare median. Kruskal-Wallis is a non-normal data test, which is going to be used only in case we have a non-random data. You click on this Kruskal-Wallis. Logic is same, but median is being compared here. Ticket closure time, factor, say ticket handler. Click OK. Here it's comparing. Look at the p-value. It is confirming that yes, ticket handler is a root cause. Yes. Null says all medians are equal. Alternate says no, at least one median is different. We look at these medians, they are like significantly different. This median, Vandana versus Nitin, they're like 2 poles apart, like 16.22 as median and 20.69 as a median. Practically, we know there's a huge difference. And is the difference huge? Yes. These are statistically significant different from each other. So Kruskal-Wallis is a complementary test, like a parallel to ANOVA, but this is for non-normal data and it compares the median. If our data is non-random, we use Kruskal-Wallis instead of ANOVA. Logic is absolutely the same. You want to use it for something else, we can use, say, manager-wise. We want to like say compare manager-wise Kruskal-Wallis. It doesn't like it's there's no. I do see difference, say 16.9 and 19.75. You may see differences. Are these differences significant? All those questions that we talked about will apply here also. Do you see a difference? Yes, and all whatever. But are these real differences? Are these are not by chance? They're real differences. Are they significantly large? The answer will be given by the p-value. And in this case, it does say no. Pretty much, these we do not have enough evidences. The differences are not large enough differences. We cannot conclude it's a root cause. So that's how we do the Kruskal-Wallis also. So logic remains technically same in all tests. We should know which test needs to be used. That's how we should be like. We would not make any errors while we dealing with these tests. Are we good with this? Shall we move to the correlation? Because that's where we will see some bit of additional information coming in. Correlation, are we good with the Kruskal-Wallis?
Can you please explain it again?
Oh, yeah.
Just for clarification, on non-random, what is the data is here?
The Y is being compared. Y is the business problem for which we are testing. Non-random, this data is random. In this case, the data is random. What if the data would have been non-random? We would have used the Kruskal-Wallis. The randomness is always checked for the Y, which is like in this case, this data is random. We had already checked this one. This data was random because all the p-values in run chart were more than 0.05. So in this case, ANOVA will be used. But if in case this data would have been non-random, then we would have used a Kruskal-Wallis.
Okay. So then for this data, we should not use Kruskal-Wallis.
Yes, absolutely. Yeah, just we're trying to go in and see when it's done, like bottom line. In this data, it's 100% ANOVA, no Kruskal-Wallis. And in case of Kruskal-Wallis, let's take another example. Stats, non-parametric Kruskal-Wallis. This is for 2+ groups. Let's say trainer-wise, we have more than 2 trainers. This says null. So the differences could be seen, yes. Are these large enough? No. The answer says no. So p-value will be the deciding factor, which will help us understand, is this a root cause or not? We will be looking at p-value and will be taking the decision. Is that okay with everyone now?
Yes.
Okay. Coming to the correlation. Now that's where we'll get some bit of extra information. So let's understand that before we do the test. Correlation. So correlation, we get p-value. What p-value tells us whether there is a relation or not. That's what it tells you. In correlation, you also get an R value. This R value is called Pearson's correlation coefficient. This R value, what does it tell you? It gives you 2 information. How much is the relation? How big is the relation, bottom line? And second, what kind of relation? And when we do look at R value, it will range like, so R value ranges between -1, there is 0 in center, and then +1. That's a range of R value. R value will range, oops, I messed up. Okay, let me just go back here. Okay, R value will range between -1 and +1. These values can be anywhere in between. So when you perform a test, some sample R values so that we can relate with it. R value can be like 0 if it's between 0 and 0.3. What it would mean that there is no relation or negligible relation between X and Y, whatever. And in this case, your p-value, this is R value range, p-value will always be null. They are interlinked sort of thing. So if your R value ranges between 0.31 till 0.75, you will say there is a weak relation between X and Y. You will always get an alternate here. If it is greater than 0.75, then you will get, this will be a strong relationship between X and Y, and you'll get an alternate. Plus, it also comes with a symbols of like sign. Sign positive will not be shown as positive, but positive sign and a negative sign. Positive, oops, negative sign. Positive means X and Y are positively correlated. If X increases, Y increases. Here, X and Y are negatively correlated. If X increases, Y decreases. let's understand some examples how we will see different values of R. Say we get an R value of 0.22, or sorry, not zero, negative 0.22, 0.67, 0.89. So this falls into the no relationship zone. So I'll just copy paste it here. No relationship. If this is the R value, that's what I will say. There's no relation or negligible relation. In this one, I will say there's a positive thing. There's no negative sign. So they will say a weak positive relation between X and Y. This one again is positive, but I will say strong positive relation between X and Y. Depending on the R value, we'll refer to the table and we'll understand how big or small is the relationship. Similarly, I can get something like this, minus 2.27, minus 0.27, minus 0.54, minus 0.91. This means same, no relation, because it falls into 0 to 0.3. This will be weak negative relation, and this will be strong negative relation. So other than the p-value, you also get to know the degree of impact, the impact factor, by looking at R value. Let's have a quick look at some examples so that we will understand what to do with this R value. In the data files for class, in the analyze folder, in the hypothesis folder, yeah, we have this file by the name of correlation scatterplot. Correlation scatterplot, we'll just open this file. Let's have a look at this one. First, for the first tab. Now, here it talks about sales and temperature. Let me just copy paste this data and like paste it in MINITAB. So your data can be of like this sales is my Y, my business problem. And this is temperature is my X. I want to check whether temperature is correlated with sales or not. This is my X, numerical X. I want to check whether temperature is impacting the sales or not. Is there a relationship? So all the confectionery industries, the beer industry and all that, like those kind of industries maintain such a data where my numerical X and Y, like both are different. If you have an X and Y, both are numerical, you will do a correlation. Let's do a correlation here. Stat, you'll go to basic statistics and you go down till correlation. Now click on correlation here. Now you don't get two separate boxes like you have been getting. You get single box. Now the first way, put your X first and then your Y. X and then like, and you can flip it, but the right way would be to put first X and then Y, and because the scatter plot will be created on its own, and which needs X first and Y second. Temperature is my X. I want to check whether temperature is impacting the sales. Yes, temperature is impacting sales or not. In results, I will click on pairwise correlation table. That's it, and just click OK. So it has created my scatter plot. I'll come back to that, but let's first scroll down. P-value of 0. That means less than 0.05. So temperature and sales, there is a relation. Absolutely, there is a relationship. But how big is the relationship? This is the R value, or this is the R value. This one is positive, yes. And this is more than 0.75. This is a strong positive relationship between X and Y. The relationship between X and Y is a strong positive one. This tells you there is a relation, but how strong will be explained by this one. Strong positive. If we look at this is scatter plot. Let me double click, it'll come up, and let's kind of enlarge this one and then understand this. So it gives you all that information here also, temperature, sales. These are X and Y coordinates. So R value is also mentioned here. What I'll do is I'll go to add item, click on this add item and go down till regression fit. We'll be talking about regression in a moment, but let's have a look at regression fit. Click on regression fit. It talks about model linear. Just click OK. You'll get you a line here. This is a regression line. We'll learn about regression. We'll come to that, understand that. But what this line tells you, line going diagonally up means there's a strong positive relationship. If a line goes up diagonally, there is a strong positive relationship between X and Y. So when my X was low, my sales was low. My X increased, my sales sort of slightly started increasing. It started increasing. My X increased, my Y increased. X increased, my Y increased. So when X increases, my Y increases. X is low, Y is low. X increases, Y increases. So there's a strong positive relationship, which is explained by this regression line, which goes diagonally up. That's what it tells me. These are directly proportional. If my X is low, Y is low. X is high, Y is high. Sales versus advertisement cost. If I put in less money in advertisement, I get less sales. I put in more money, I get more sales. I put in more money in advertisement, I get even more sales. So strong positive relationship. They are correlated. This is for positive correlation, but you can get different kind of data for this. Let's have a look at another example in here. So you have second tab, which says negative correlation. This kind of data is maintained by the second-hand car companies, which deal with selling the cars and all that. So I would like to know what kind of impact will have the age of the car will make a mileage of the car. So age of the car versus mileage of the car. So I have collected some data and I would like to check whether there is a relationship there or not. Stats, basic statistics, and correlation. What's my X? My X is the age of the car. The car gets older. What will it do with my mileage? Results already checked, pairwise correlation. Let's have a look at it. Let's scroll down. There is a relation. Yes, they are correlated. How they correlated? It says negative 0.967. Strong negative correlation. If my X increases, it reduces my Y significantly. Negative correlation. And if I look at the scatter plot, have a look at this. The line will go diagonally down. That was going up. This is going diagonally down. The car was new. The age of the car was like it was new car, was giving a better mileage. As the age increased, my mileage reduced. If X increases, my Y reduces. This is negative correlation. So your X can be and Y can be positively correlated, negatively correlated. When you look at the scatter plot, it'll tell you the picture also. Plus these signs and these numbers will help you understand. It gives you the correlation coefficient also. Yes, you can, other than this, get something like this, which is, so you may not always get these lines just like that. But yeah, different ways you can look at data. I want to check whether there is a correlation between the hours work, the number of hours I work versus the amount of money that I earn. So stats, basic statistics, and we go down till correlation back again. So hours worked is my X, and I want to check whether it impacts my salary. Click OK. I will check this out. Let's say this is null. No relation established. If we look at this one, this is in the no relationship zone, 0 to 0.3, no relation. That's what it tells me. It comes with a negative, but in a negligible way. So we click on this. It tells me the same story here also. Let's look at this. Add item, regression fit. Well, sort of, it's not going down. It's like sort of flat line. It doesn't have a relationship. Like somebody's working 63 hours is making 23,000. Somebody's working 90 hours is making 49,000. Somebody's working 169 hours is making 21,000. So it doesn't seem to have a relationship between the hours worked versus salary. Say, look at this. They are all in the same line, but somebody's earning like for similar hours, 221 hours, 30,000. Somebody's making like really high in this case also. So hours and salary doesn't seem to be correlated in this case. So data can give you different kind of outcomes. So you can't control the outcome. Yeah, whatever data you get, you can see the outcome in multiple ways. So you get to see whether there is a X and Y relationship impact or not. For numerical X's, you do a correlation plus scatter plot. Is that clear? Correlation to everyone?
Yeah.
How about others? Like, just let me know. So we pretty much that will conclude the analyze phase. We'll be left with one more statistical test that we will cover up today, which is regression. But yes, before we go ahead, just want to be sure we understand this. Is everyone okay with it?
Yes.
Yes. Okay. So with that being said, like with whatever data you have, like you will be able to perform your test and understand like which one are the real root causes. The ones which are real root causes, you'll move with those root causes in your next phase, in the improve phase, because now you know there is an impact and you would like to kind of work on the root causes and improve the problem, business problem. There's a statistical relationship that you have been able to figure out. It's no longer my gut feeling. They have been proven. Now, so pretty much the ones which are null, I'll just junk them. There's no need of looking at them. There's no relationship with those x's and y. So practically that's junk for me. I have cleaned up the mess. In the improve phase, first thing first, see, in improve phase, our work as Six Sigma professional becomes relatively very low, because the core technical experts, the process experts will take the front seat and we will take the back seat. Why? Because the reason why you started a Six Sigma project is because you had no clarity as to what is causing the problem. And that is why you needed a Six Sigma project to be done, to get you an exact clarity as to what is impacting and what is not. So when you tell the business owners, the process owners, the subject matter experts that these are the real root causes, validated one, no longer gut feeling, well, they will have an answer for you. We'll learn about what's there in the improve phase, but yes, before we hand over, we would like to further add some more details to give it to the process owners, which is where we want to understand. See, root causes you may have found, but not every root cause is equally important. Some root cause may be very important, some root cause may be lesser important. So I need to know how much each root cause is impacting the business problem. So this will be a great insight for the management or the subject matter expert to prioritize and like channelize their efforts and energies based on the impact factor. Somebody is impacting, say, 90%. I would rather work on that, not on the one which is impacting 10%. So I would like to know which one is more important, which one is lesser important. The answer to that will be regression. So now regression, we will study two types of regression. One is a simple regression, and second one is multiple regression. So simple regression, we test one X with Y at a time. Multiple regression, we test multiple X's with Y at a time. We get a p-value because one X will give you one p-value. Here you get p-values, multiple p-values for all those X's. Here you get R square. We'll understand what is R square. Here we get R square adjusted. Here we get linear equation. And here also we get linear equation. Now, we will be skipping the linear equation here because we will be kind of covering up back again here. So rest we will kind of cover it up because this will get repeated in the multiple part. So for that, we have a small data set that we can look into for, like, it's in the improve phase folder. There's a file by the name of regression. So we'll open up the regression file and let me just quickly copy paste this data and kind of explain this on. Let me go back to MINITAB. Okay, we got the data, but before we perform the regression test, let's kind of understand what are we doing here. What's the purpose, like what we're trying to establish here. So this is about some recruitment firm who is trying to come up with some mathematical model through which they can offer salaries to their candidates, to the people who come for job interview during the recruitment process. They do not want to have a gut feeling based, let's offer $10,000 to this person, 11,000 to another, 15,000. Is there a reasoning behind it? Like, do you want to have some sort of statistical way to predict the why, which is in this case salary? They want to offer salary. So this sit down and like sort of introspect what are the what could be the possible factors. So some people believe that gender could be a factor which could decide the salary. Some people feel that these are subject matter experts who are kind of sharing these possible reasons. Like some people feel male get better salary, some people feel females get better salary. So I don't want to have any, I don't want to kind of create any sort of like preconceived notion. So I've included that as a factor, gender. Some people believe that how well do you do in your interview? Well, that will definitely impact your salary. So so probably we have some sort of scoring mechanism. We have some test on we score somebody on a scale of 1 to 10, and that's how the scores are derived. We have a hiring process. So that's what also drives your salary. Some people believe no, your experience matters. So how experienced you are, that could be a big deciding factor in your salary. So you would like to understand which one is the real root cause A that can be used. Regression can be used for that. Other than that, it also helps me to understand and predict the Y salary. So what they did is they looked into historical files. These people were hired at some point in time. We want to look at historical data and make a model which will help us in future. So they got into the historical hiring files and they saw that somebody was offered some salary, say 88,000, whatever, some salary here. She was female. Whether these people are working now or not working with us doesn't matter. But once they were hired, when this female was hired, she scored 4.5 out of 10 during the interview process. She had 11 years of experience when she joined. Somebody was hired with 77.3 as salary, whatever value it may be, male candidate who scored 7.8 when at the time of hiring and had 6 years of experience. So these people may be working, may not be working, but we got into our historical files and we have got collected the data now. So we start with simple regression first, and we would like to understand about the data here. So simple regression, 1x with y at a time. So we go to stat, regression, and fit regression model. So stat, regression, and fit regression model. Now, here I have an option of response, which is my y, which is salary. That's what I want to test. It gives me an option of testing both numerical as well as categorical. So continuous predictors will have numerical X's. Categorical predictors will have my categorical predictors. 2 group, 2 plus group, everything will get in here. So first thing first, 1x with it at a time. So continuous predictor. We have 2 numerical X's. We have got interview score. We have experience. Let's see interview score. So interview score on salary. That's what you want to check. Click OK. We get the test results here. Let's understand. This is the equation. I said we'll skip it. We'll complete this again in your multiple regressions. We're going to skip this regression equation for now. Interview score, p-value, that confirms yes, there is a impact. Yes, there is impact. And go further in analysis. ANOVA also gets covered here. So it confirms that yes, interview score has a significant impact on your, it has a relationship. P-value confirms there is a relationship. Yes. Now we have R square. So we talked about 3 pieces of information. We were looking at p-value. Yes, we got the p-value. It was impacting. Yes, p-value. We got R square. Let's write down interview score R square, which is 52.98%. 52.98. 52.98. That's for interview score. This is all R square. Now that's what we have. So we had 3 ways linear equation we're skipping, and which ways? Let's go back here and change the X. So I'm removing interview score and I'm picking up experience here. So I want to check now experience versus salary. Now I get my test results. Equation I'm skipping for now. P-value confirms there is, yes, there is a relation. P-value, it's an alternate, confirmed. R square, 83.26. Experience, 83.26. That's what it says. 83.26 is R square. P-value, we got p-value, we got here. Equation we're skipping. That was for experience. We left with one more. Now we're done with the numerical ones. Remove that. Categorical. We just have a gender here. Just click gender. in the categorical one, click OK. Let's go back here. We are going to skip the equation for now. Gender, we got a p-value here, null, not impacted, not correlated, simple. R square, 10.06%. Gender, 10.06%. Now, what is this R square? Now, in a statistical way, if you want a technical way, it explains the degree of variability X explains X contributes basically in Y, or basically X whatever in little term it means that how much of impact X makes on Y. Basically what is the contribution component, how much of Y is dictated or controlled or basically explained by X, how much of Y is explained by that X is explained by this R square. So it tells me that interview score, the factor root cause, interview score controls. So we got an alternate here, alternate, and this is null. So this impacts the salary decision by 52.98%. This is the impact of interview score. How well do you do in your interview is impacted, like how much 52.98% impact on the decision of how much salary will you get will be, the impact from interview will be this much. Experience has a bigger impact, like 83.26% of impact goes from the experience part of it. Null, we get like if at all this 10.06% makes some sense or has any kind of impact, this is all it is. Null says no relation, but like how big is this 10.06? We'll understand in a moment. But yeah, whatever it is, this is the impact factor of 10.06 with respect to gender. So this explains how much of X impact X makes in Y. That's what my R square talks about. Coming to multiple regression. Now, we may have a lot of X's, but it's advisable that when we're doing multiple regression, we should test maximum. Not kind of, otherwise it becomes too clumsy for you to kind of read the data. You can do it in batches if you have a lot of them. So you will, by the time you get into an improve phase, you already have filtered a lot of X's. So you have very few X's. You do not have too many of them. So, but in case you have too many of them, you can use in batches. So here I have got 3. So I am testing all the 3 here. Click OK. Now let's read this. We tested all the 3 X's here. This is interview score, p-value, p-value, p-value. So bottom line, we're getting, this is null. Gender is null. Not impacting. These 2 are impacting. So we getting the p-values, yes. R square adjusted. Let's have a look at R square adjusted. 88.84. So this is for R square adjusted is 88.84. This is what it says. Yes. Equation will come back. Equation is right here, but we'll come back to that later. Not right now. It's not yet cleaned up. We have to clean up this model. Now, technically, I know the impact of every factor, but bottom line, what is this R square adjusted? What does it mean? Now, I know interview score impacts 52.98, experience impacts 83. Gender, if at all has any role to play, it is impacting 10.06. But during the interview, the person is appearing for the interview, all these factors are influencing the salary decision at the same time. So we know the impact factor of interview, we know the impact factor of experience, gender, every force is impacting the Y, which is salary at the same time. But what is my overall impact of these factors? Because some factors may be positively impacting each other, negatively, we already talked about correlation. Some may be positively impacting the other factors, something may be canceling others' impact. So what is my overall adjusted impact after all these forces are acting together? What's my overall impact? This is what is explained by R square adjusted, the overall impact of the model. But now I want to see how much each factor is impacting or contributing. Let's kind of do one thing. I will remove one factor, experience here, just to see how Big is this factor. I removed experience. Now we go back to Excel. So I'm trying to see loss of experience. If I remove experience from the model, how good is the model now? Let's look at R square adjusted. 55.74 R square adjusted. 55.74. The moment I removed experience, my quality of the model, the predict quality of the model has dropped from 88.84 till 55.74. There's a drop or a significant drop in the quality of the model by 33.1%, which is a very, very significant factor. Why? Because it was an alternate one. It was impacting, it was strongly impacted. And we also know there is a huge impact factor here. So it was impacting the overall decision a big by big margin. Let's put it back and see, remove the interview score and see what is the role of interview, put the experience back and interview score. So we losing interview score and see what is the role it has to play in the overall decision. 82.43. If you remove loss of interview score in the model, it's bringing me down to 82.43. Well, what is the loss from the initial model? 88.84 minus what we're losing, 6.41%. I'm not saying it's a small one. It is relatively a big drop in the margin, but not as big as experience. So this experience is definitely a very, very big critical factor as compared to interview score, but this is both are required. Let's put it back because it's an alternate one. It has role to play. Let's see how much gender is impacting the overall model. Remove gender, loss of gender, 88.78. Loss of gender in the model, quality of the 88.78. That's what it says. This minus this. This was the overall role of gender in the decision factor. And hence, we would like to kind of get away with this. This is chunk. We've reached a clean model now where we only have only alternates will be entertained in the end. That's how it looks like. Yes, interview score and experience both are alternate. We have a clean model without any junk in here, which is 88.78 is the overall quality of the model. So that means you can predict the salary of the process for anyone. How much of that can be predicted? 88.78% of the whatever salary you're predicting, 88.78% of salary can be predicted by these two variables. And this is how it tells you how good is the model. Higher the R square, better it is. So it means that you've got real impacting ingredients of salary decision. What controls salary? 88.78% of salary is controlled by these two factors. Now we coming to the equation. That's the reason we wanted to come to this clean model sort of thing. Now we can look at the equation. Salary. So I'm just kind of writing it down. The final clean model salary is equal to 53.22 plus 1.754 experience, 1.754 of experience plus 2.105 interview score. 2.105 interview score. That's what it says. Now, how do I make sense out of it? For bottom line, I am trying to predict my salary with this model, the model mathematical calculator that I've created here. It works on the equation for linear equation, which is y is equal to c plus mx. Y is your salary, what we're looking at. Y is your salary. C, in a statistical way, we call it as intercept. And in a layman language, we say, yes, it's a constant, you can say constant value. But what does it mean? It is the minimum value of y in absence of x. Minimum value of y. Bottom line, when the value of x is 0, the value of y will be c, and we'll look at it. We'll just see that in a moment. M in a like a statistical language, it's called a slope, and in a layman language, it's a multiplier of x, and x is x. So bottom line, x is the factor. let's understand how the same stuff here. Salary is what we want to predict. It says 53.22. This is constant value, which is C. 1.754 is the multiplier 1. Multiplier, because there are two factors. First multiplier of what? Experience. So this is going to be the experience factor. This is the X1, which is experience. Then whatever is the product, it's 1.754 multiplied by the experience. That's what 1.754 experience means. 1.754 multiplied by the experience will be here. So, and then it says 2.105 multiplied by interview score. So this is X2. This is multiplied to, and this is X2, which is interview score. Now, how we will predict the salary? It says 53.22. Whatever is the product, 1.754 multiplied by the value of experience will come here. Then it says 2.105 multiplied by the score of how much you score in the interview. And if you look at all these, they are getting added up. 53.22 plus whatever is the product of 1.754 plus whatever is the product of 2.105 plus, all these three are getting multiplied to give you the salary. Now the calculator is ready. Let's see how it works. Somebody comes for a job interview, and this person is an absolute fresher, has no experience, just out of college, 0 experience. Value of experience, 0. So 1.754 multiplied by 0 gets you 0. Nothing changes here. You don't add up anything to the constant value. The person scores 0 out of 10 in the assessment. So nothing adds up here also. So this also gives you 0. So it says this, when the value of X is 0, or in the absence of X's, this will be the minimum value of Y. Y will remain same as constant. So 53.22 plus 0 will give you base salary here. This is the minimum base salary that you will be offering to your candidates. Now, somebody comes in with let's say 5 years of experience. Well, so 5 will get multiplied by this and will give you a plus factor, because this is getting plus from this one, and scores 7.5 in the interview. That's the multiplier for this, and you get this, everything get multiplied here. That's the salary, which is ready. Somebody comes in with a 9 years of experience, scores 2 out of 10 for the salary. So bottom line, I have created a calculator which is helping me predict the salary. This equation was created from my data itself, historical data, and I'm using my historical data to predict future salaries, future problem, business metric, which is salary in this case. So I will be able to use this, and how confident I will be about these salary predictions. Like technically, I am sort of 88, whatever this 88.78%, because I'm removed gender. So I've got clean model, R square adjusted. So technically, I'm like 88.78% of the salary decision is like explained or controlled by this model, which is pretty healthy model. So pretty much I am, based on historical data, I'm able to predict the salary. Now, given the fact like this can't be used for like any other, so this is particular for that organization where from which the data was used for creation of this model. It cannot be used for any other company. So what if somebody comes with a 35 years of experience? Sorry, that doesn't work here. Why? Because do you have any 35 in your model, in your sheet? Well, I've closed it. Don't have 35 years here in this column. No. So this model will only help you between range of minimum and maximum of the data set, because it was used to create that particular. So the equation was created keeping all the values in mind. So the maximum, I think it's 20 here, or 20 or something like 21. I can see here. So 21 till the age of 21, I can predict the salary. So it is going to be good enough until the age of 21. Say somebody comes in with a higher experience, well then please add in the data, create a new equation, then you can use it. But till that time, you got to look at the basic. You can't just use this for anything, because that kind of values were not used for creation of this equation. It will continue to give you good, reliable information till the time you are within the limits of the data. It was like whatever data maximum minimum it was used for. So that's how the regression model works. People use such calculators for predicting various business metrics. People have created attrition calculators and so on and so forth. So again, you go deeper into it. Regression is a very, very vast topic, but yes, the basic beginning of regression is always a linear regression. Again, it goes deeper into it, but practically the stepping stones will be here. We need to understand, because regression is a very, very powerful tool. It helps you uncover a lot of aspects of the data. You will be able to predict things, and ultimately what I'm looking for is to get into the Six Sigma project is I'll be looking for this information, because based on this information I will be sharing these details with the subject matter experts to look at it, and accordingly work on the action plans or strategies, emphasize more on the factors which have higher R square, and lesser on the ones which have low R square. So that's how the regression thing is covered. Yeah, questions if you have. Anyone has questions around the regression part? Anyone? Yeah. I would request you just confirm. So,
do we regularly use regression in the projects, or it's again depends upon the situation?
no, we use it. We use it in improve phase. See, one thing can definitely come in like this. We can definitely counter a question. Why can't we use this in the analyze phase? Why are we talking about this in the improve phase? Why even take a pain of doing a correlation, then two sample T, ANOVA, and all, when you have an option of testing everything, two groups, two plus groups, you can test everything, right? So you have an option of doing everything. Why even care for ANOVA, two sample T, everything? See, when you do those testing, you get to get the details of every X, whether male or female. Here you just get the p-values. Regression will be used in the improve phase, because once you've cleaned up the junk, you've cleaned up the mess, and then you've got the real validated root cause, you really want to make sure that improve phase, when you want to go and really start the work of improving the business problem, you should know which ones, because you do not have ample amount of time, money, because the management, the moment they know that you have got the real root causes, pretty much they are very low on patience. They want to see the results as soon as possible. And from that perspective, yes, you should know where to put your efforts, on which X you need to put more effort, which X you need to put less effort. So regression is a tool that is we use in the improve phase for sure, just to get an idea about which X needs to be prioritized more and which one needs to prioritize less. Because accordingly, we'll put more people, more effort, more strategies on that X, and lesser on the other ones, which has probably very, very low R square. We'll probably not prioritize them as much. It is going to be used for sure. Regression we use, be it a green belt or be it a black belt kind of scenario. In black belt, it gets even more complex when we get into the design of experiment, because even design of experiment, which is used in DMAIC, that uses regression. So regression is going to be used predominantly going forward also. Yeah, questions? I hope that answers the question that you had.
Yes, sir. Still, my clarification is, suppose a project is going to be there. We'll be using both analyze all that thing and also on the improve phase, or it's again depend upon the project which we are taking.
See, analyze phase, you technically will be using the same test. So you, once you're done with the analyze phase, you are in the improve phase. And improve phase, you know the problems which have been identified. You can straight away go ahead and work on the strategies, take help from subject matter experts. Again, nobody is stopping you. There's no regulation or no rules as such, but it's good to know where to put your effort more. So but yes, analyze phase, you must do those tests for correlation to sample ANOVA to know which ones are the root causes. And once you know that, see, you may ignore regression also because you know the root causes. Subject matter experts would know, okay, what to do. You'll do a root cause analysis there to understand what went wrong in a particular root cause. So practically, you can still work without that, but I would recommend, like, it's a barely, it would take any time for you to kind of, because the data is available with you. It's just a matter of doing a regression test. It won't take much time. You can still do it, but yeah, you may choose to ignore also, but that's not, nothing is like, it's not a showstopper. Like you must do it, but it's good to do it.
Okay.
Okay. Any other question? Okay. All right. So
Can we get some more example on this? Some data you can share for
yeah, I will.
regression.
I'll share. Like, says there is one file in there. Like, so before, like, that's what I wanted to kind of check with everyone. So data files for class. There's one file in here in the analyze phase. Have a look at this, and so I just want to kind of talk through this hypothesis test folder. Now, first of all, I would strongly recommend everyone to try out these sample data tests. So 2 sample t tests. Let's first look at it. This file has a lot of other data, random data. So this is one way of plotting the data. Say we all are used to this kind of data. Let me quickly show it to you. So you have this kind of data. This we are already used to. How to test this 2 sample t test. Let me quickly go back here. Okay. So you have Y in one column. Say there are 2 hospitals being rated. This is customer ratings being given by customers, different customer satisfaction ratings for 2 hospitals, A and B. So which test I will use? There are 2 hospitals. We're comparing the ratings of 2 hospitals, 2 sample T. So we are used to this particular data set when the Y is in one column and X's are in one column. So we have this method. We use 2 sample T. Let's go and do a 2 sample T test. So we can use the 2 sample T, rate and the hospital. We do the test the way we have been doing it. So we get to know p-value. Same process, the way we did 2 sample T. But now the data can be presented this way also. Rating of hospital A versus rating of hospital B. Now, how do we do the test? Copy paste this data. Go to MINITAB and let's say, go to stats, basic stats, 2 sample T. Click on this 2 sample T. It says both samples are in one column. No, now they are in different columns. The way it is always like this, each sample in its own column. Sample 1, sample 2, A hospital rating and B hospital rating. Click OK. Same steps, but you don't have to kind of recreate the data for yourself. So you don't have to, if I get data like this, I can do one thing. I can, if I'm comfortable, I can do this. This is also, but I would practically, MINITAB gives me the option of testing it the way I get the data. I don't need to kind of recreate the data. Or this is B, which I want to avoid because I have an option of testing it the way it is. Plus, I have another way where I can group this data like this and like put it back into the original format. Let's have a look at this. I have data in 2 separate columns. I want to make it in a single column the way we have done it. So it's like I can club them together. I go to data. It says stack columns. You want to stack them up together. Stack columns. What do you want to stack? Stack A and B together. Okay. Say hospitals and rating. All hospital A and B rating, they've been stacked together. Now, if I want to break this down into 2 separate columns, I go to data, unstack column. Now I want to put them together like a separate column, unstack data. What do you want to unstack? I want to unstack the rating by hospital. Hospital A rating, hospital B rating. So you can convert the data the way you want, or you can use it as it is. You don't like, because MINITAB gives you the option of going to that filter. There is a lot of data like this. You can practice, say, there are two sample T tests, in-house audit score versus customer audit score. You want to compare and see, is there a difference in the way we do audit and our client does the audit? 2 sample T. rating, hospital rating data. There are two, oops, let me go back to this. Okay. Weekdays versus weekend processing time. You can test this, 2 sample T, product, 2 groups, 2 sample T. So some data is already there, which you can practice on classroom and e-learning score marks, exam scores. You want to compare 2 sample T test, some practice you can get from here. Let's go back to other data fold, other files. ANOVA, same process, same method. ANOVA, you can look at some sample files. Same method, you can do it with this one also. 3 groups, 3. You can convert them or you can use it as it is. Some data for you to practice on multiple data sets. Correlation, we have already worked on this file. And once you're done with everything, please go to random test once you're done with everything. This is a random file that you can work on. This is your Y. This is your Y, and rest everything is your X. These are your X's. So once you're done with various testing, then you go for these X's and test which one is root cause, which one is not. So this one will have so you have to follow all the steps which we discussed. You have to start with your normality. You have to go to randomness and perform the test accordingly. So on this particular spreadsheet. Is that okay for everyone? I hope you got it, getting it.
Yeah.
Okay. So you have all the data files in there, like in the analyze folder, hypothesis test. Just go through them, at least get used to the 2 sample T and over correlation and all those other tests, and then go for the random test, because random test you'll get to practice everything from the beginning till end, and you have a random data set which has all different types of variables. So you would have to check and decide on your own when to use a 2 sample T, when to use ANOVA or Kruskal-Wallis or correlation. You'll end up doing everything as like normality, run chart, everything will be covered in that random test. I hope we're good with everything, like for now.
Yes.
Okay.
Yes.
All right
Okay.
then. All right. So give me one quick moment before we call it a day again. I guess it will be good to kind of quickly share the file in case you can download it right now. Any which is I'll email, but people who can download, it'll just give me one quick second. I will just get this done. I'll just share it right away so we know.
Normally, we are getting the recording video only not on this file.
Excel files you have not been getting.
Yes.
No, okay. So like I've just, you can click on it. It's from day 1 till now. All the files are, you can click on this. It will open up. You can save this file on your system. I will, because I will be emailing this file to IMC or, again, so for them to circulate it. So that's how, just to make sure that nobody gets missed out, but still you can click on it. It'll get downloaded. I'll be emailing the same file to IMC so that they can circulate with every participant. Same file. This has been like from day 1 till now, everything that we have worked on, it's in the same thing.
Okay.
Okay. You might also receive this from the IMC team because I will be sharing the same thing with them. I guess that is going to be all for today. Let's then catch up next Saturday and then for the final session then. Until then, please do take good care of yourself, and let's see. And if in case you have any questions, please do post it in the group.
May I ask something?
Yeah,
Suresh?
sure.
Yeah, after the last session, what we're going to do after that?
After the next session,
Yeah.
you'll go through the assessment, say some sort of preparation, then the assessment part of it. So that's how it, like, I think like that's how it goes. But yes, I'll have somebody like from the IMC team to kind of coordinate and tell you what's the journal, like the process. But again, technically, once you this is completed, then you go for the assessment part. You can prepare. There's some sample test also. Then you go for the assessment thing.
Yeah. Okay. I see.
Okay.
Thanks.
All right. Thanks then. All right then. Thanks everyone. Thanks for your time.
You.
Thanks. Bye-bye.
Bye.